Good morning, ladies. Uh, I welcome you all to the first lecture of integral calculus. And I hope your preparation for board examination is going all right. And what about IITJ? All right? Okay, I hope you are making notes. Okay. So before I start integral calculus, I normally when I ask my students that why are we studying calculus or why are we studying complex numbers or any topic of mathematics, whenever I ask them, uh, I the answers which I get mostly is like so that because of my examination I'm studying that probably that is in the syllabus of examination, that is why I'm studying that. But that is not the attitude regarding mathematics. When we are studying something in mathematics like complex number, like calculus, it has more to do with the practical life, it has more to do with your professional life, it has more to do with your future than to just for your examinations. Okay, so let today we are living in the world of science and technology, right? Today we are living in the world of science and technology, and we see a remarkable progress in this field. And you know the major force behind this remarkable progress is mathematics, and the branch which actually responsible for this is the branch of integral calculus and differential calculus. You see various fields of physics, chemistry, geology, biology, medical sciences, statistics, economics, even in social sciences, the most of the problems are being solved by the application of calculus. Uh, let's say by what speed a rocket should be propelled upward so that it never comes back to Earth. Or let's say a strain of bacteria, let's say it propagates at the rate of its amount. And let's say at the end of 1 hour, it doubles itself. Then at the end of 2 hours, by how much it will increase. Or let's say the design of aeroplane, a huge metallic object being lifted in the air. Or let's say a certain force is acting on a spring and it is stretching it by 1 inch. So how much force it needs to stretch it for 1 feet. So you see, I have chosen various problems from various fields. And the solution of all these problems lie somewhere in the routine, more or less routine applications of calculus. But frankly, I tell you, calculus is not just a technical tool. It is more of a collection of fascinating and exciting ideas which have intrigued uh, thinking men for the last centuries. Let's say it talks about the concept of speed. It talks about the concept of mm, rate. It talks about the concept of growth. It talks about the concept of area, volume, continuity. You see, so these concepts, these calculus forces us to stop and think about these concepts. And the another amazing part about calculus is that it it unifies everything together. It unifies everything together. Let's say if I talk about calculus, calcium, calculate. If you see these three words have a origin, have the same origin. Of that, these are the same. The Latin word is calculus, and which has the same origin, which means what does it mean when we say calculus? What is the meaning of calculus? It means small pebbles, small pebbles. And you know, at one point of time during ancient time, it was pebble which was used as a counting tools. We used to count with pebbles. Okay, so let's say there is a curve C, and let's say there is this baseline. Okay, this is a horizontal baseline you see, and there's this curve C, and I'm going to assume that in this C, the vertical lines will not cut this curve more than once. Okay, that is the definition of function. You know that. Okay, now let's say I want to assign a number to this area. Okay, this first problem, the calculus which answers it, that I want to assign a number to this shaded region, and I want to assign a number to the steepness of this tangent. So the first thing which assigns, which deals with the solution which deals with the problem of first problem, that we have to assign the number to the area, which represent the area. That branch deals, that is called integral calculus. And the second branch, the second most important branch, which talks about, which assigns the number to the steepness of this tangent, is differential calculus. So this is the difference. Okay. And the thing which connects them, the differential calculus and the integral calculus, is fundamental theorem of calculus. Okay, so we are going to talk in a few minutes. So, but tell me, since you have started studying calculus, first you studied differential calculus, right? And then you are now graduating to integral calculus. But do you really think that this is the way calculus was developed historically? It was first integration which came, and then the differentiation. I'll tell you how. This calculus, the first seed of calculus, was put on almost 2,300 years back. At that time, Greek mathematicians were trying to find the area of various figures. They were knowing how to find the area of polygon, but they were trying to find the area of circles, parabola, and other curves. So what they were using the method of exhaustion. The method of exhaustion talks about, let's say I have to find the area of the semicircular region, okay? And first I'm going to draw a trapezium. This is a polygon, okay? You can see trapezium. I can easily find the area of trapezium since we know how to find the area of polygons, right? So I can easily find the area of trapezium. So I get approximately the area of semicircle is approximately equal to this trapezium. Now I want a better approximation. So I'm going to increase the number of sides of this polygon. So I'm going to make more number of sides, and I'm going to increase the sides as till this area exhausts up. That was method of exhaustion, and it was Archimedes who actually was very successful in finding the exact area of circle and parabola and various other shapes. But after Archimedes, till 18th centuries, 1800 साल तक there wasn't any much remarkable progress in calculus. But in 16th century, suddenly we accepted the Hindu-Arabic numericals. You understand Hindu-Arabic numericals, the numericals which we use? We left the cumbersome Roman numericals. Then we also introduced plus and minus sign. And then decimal system also cropped in. And then Italian mathematicians like Ferrari and Tartaglia, they found the solution of cubic and quartic solutions. You know, cubic and quartic solutions. So this actually stimulated the work of calculus again, beyond the Archimedes point, right? And in 16th century, other development also happened in algebra and calculus, and mathematicians like Pascal, the Wallace, Fermat, they all they developed a fragmented part of calculus. But the real success happened in 17th century. The method of exhaustion, which ancient Greeks were using, got a remarkable success and named as an integral calculus by the mathematicians called Mr. Isaac Newton and Mr. Leibniz. So from 17th century, the branch named as integral calculus, and in 19th century, the mathematicians called Mr. Cauchy and Mr. Riemann, they put it on a fundamental mathematical principle that we have to study calculus as a mathematical subject. And today also in the work on calculus is going on, right? So this is how the basic history, how calculus is growing and how it is important and why are we studying it. Okay, now, so we'll now get back to our integral calculus part. So let's say integration, right? So let's say I have a bigger problem. I have a big problem and I have to solve that big problem. So I'm going to chop that big problem into smaller pieces, right? And then I'm going to find answers to those smaller problems. And then I'm going to integrate those smaller answers into one big so that I can answer my bigger problem. So this is the idea of integration. Okay. Now, there is also an ancient saying that it is easier to destroy than to create. Okay, it's easy to rip a paper, but it's very difficult to unrip it. So let's say mathematically also it is very true. It's quite true. Let's say I say multiplication is easier than anti-multiplication. What is anti-multiplication? Factoring, not dividing, but factoring. Let's say I ask you to anti-multiply 991. When I ask you to anti-multiply 991, how are you going to do it? What will be the answer? Anybody? Any guess? It will be, I'll tell you, it will be 97 into 103. Like, how you would have reached to the answer? By looking into the prime numbers, right? 2, 3, 5, 7, 11, 13. So it would have been a big thing. Or maybe you would have guessed, okay, it is pretty close. It's a square root is pretty close to 100. So I'm going to look the prime numbers which are pretty near to 100. So you would have got the answers. Fine. If I ask you to multiply, if I would have given you to multiply 97 to 103, you would have done it easily, right? So you see, multiplication is easier. Now let's say I think of a prime number of 10 digits in my head, and I give you that 10-digit prime number, and I think another 10-digit prime number and give you that also, and I ask you to multiply. You will be able to multiply it. It will take some time, but you will be able to multiply it. Like, let's suppose I think a 20-digit prime, I think a prime number of 10 digit in my head, another prime number of 10 digit in my head, and I multiply it in my head, or I multiply it not in front of you, and I throw the product in front of you, and then I ask you to anti-multiply it. Will you be able to anti-multiply it? No. So probably it will become my signature that only I know the answer. And maybe if I go beyond 20 digit into 20 digit, I'll be the only person. Right? So it becomes my password. That who am I? I am the person who actually knows the answer. So that becomes the password. This is the way things work, right? Now, similarly, the integration and differentiation thing. So when we talk about when we talk about indefinite integration, I'm also going to say it as anti-derivatives. Okay, I'm going to call it anti-derivatives or anti-differentiation. So you see the idea, anti-differentiation and differentiation. So you see the connection. It's just we have to do a reverse thinking. So since we saw anti-multiplication was also a reverse thinking and it was pretty difficult, in the same line, anti-differentiation would be a difficult task, because when we were doing differentiation, it was like more of a mechanical thing. We were knowing things, okay, these are the functions, we will be able to differentiate it. Since we know the function and we know those mechanical tools, how to deal with it, how to differentiate things. If it's a polynomial function, we know how to differentiate it. If it's a trigonometric function, we know how to differentiate it, right? So similarly, let's say, so basic definition of integration, if I say, let's say, if I say fx dx, I'm symbolically, it means that I have to anti-differentiate this fx. Means I have to find a primitive function or a father function whose differentiation is this. So I can say this. We are going to symbolize this with a funny S thing, right? Okay. So this is the way we are going to symbolize it. Now, why C thing is there? Because when I ask that, let's say, integration constant, why? Because when I ask you to differentiate a function, there is a one answer. But when I ask you to anti-differentiate, can I ask you what is the anti-differentiation of this? Or I have to ask what is an antiderivative of this function? And because if you see, if you differentiate x square, what will be the differentiation? 2x, x square plus pi, x square plus any constant. See, right? So this is how when we are going to ask the antiderivative, we are going to say an antiderivative, not the antiderivative. Okay. Now, since we have to do a reverse thinking in, so what was the first rule in differentiation we learned? That the derivative of a sum is sum of a derivative. That was the first rule of differentiation. Similarly, in antiderivative, the antiderivative of a sum is sum of antiderivatives. So we can say, let's say I have two functions, fx and gx, and the antiderivative and the different derivative of this is fx and gx, right? So I can say that fx plus gx dx is equal to fx dx. You can justify this, just it's anti-thinking, right? Now similarly, let's say I have to anti-differentiate x to the power n dx, right? I have to anti-differentiate x to the power n dx. So first, I have to think of a function whose derivative is this. I'm going to say n is not equal to -1, right? So I have to think of some function whose antiderivative is derivative is x to the power n. So I'm going to make a first guess, and I'm going to say, okay, fine. It looks like x to the power n plus 1. I'm going to think this way. Now, when I think this way, I know how to differentiate any function. So I'm going to check it because differentiating is easy. So I'm going to check. So when I differentiate it, I get n plus 1 x to the power n. Okay, pretty close. I'm pretty close to this thing, right? So I can say my answer would be. So how you're going to justify this? Remember when we were constant multiply jab ho raha tha, when we were finding the differentiation of a kfx. So when we were finding dy by dx, what was it? K into f prime x. So we are going to justify this also, right? So we can say x to the power n dx is equal to plus c, right? So we got another rule, the constant multiplication rule. Similarly, जिस जैसे derivative में करते थे, वैसे ही we got the constant multiple rule. So now we can easily, now since we know x to the power n is x to the power n plus 1 upon n plus 1, provided n is not equal to -1, n can be any rational numbers. Any rational, it's true for any rational number, right? So now this thing goes fine with it. Clear? Now this is the first thing which we developed about x to the power n, and now we will be able to handle at least the polynomial functions. We will be able to find the antiderivative of polynomial functions. Okay. Should I erase this? Now let's say I have to anti-differentiate one to the power x dx, right? So what will be the answer? We'll think that it was, we used to find something like ln x. So I am going to make a guess that ln mod x, right? And when I am differentiating it, I am getting the answer fine. So I can say, okay. Now, do you really think that this constant doesn't depend on x? See, when I say log mod x plus c, it means ln x plus c for x greater than 0, ln minus x plus d x less than 0. So aren't my constants are changing? So we can say that this is basically the graph of ln mod x and ln x plus c. अब मैं किसी को भी up and down जितने भी इससे कर सकता हूँ. So I can push up this function till here and I can pull down this here till here. ठीक है, तो sadly in most of the books we find that it is written c as a constant, but it is actually a local constant. Understand? It depends on the x. If x is positive, it is c. If x is negative, it is d. It can be equal, yes, it can be equal, it can be different also. So are these constants are not changing? They are depending on x now. So these are basically a function of x now. So, but mostly in most of the books, it is written as a constant. So till IIT JEE, but whenever the questions comes on a true or false basis in IIT JEE, so you can actually handle this, right? That is the idea why I shared this thought. Okay, clear? Now let's say I have to anti-differentiate some trig functions. Okay, we have done polynomials, we have done x to the power -1, right? Now let's go to trigonometric functions. Let's say I have to find integration of cos x dx. So I'm going to make a guess that, okay, fine, it was sine x. So sine x plus c. It's fine. It was not difficult for me to guess. Now similarly, minus sine x dx wasn't difficult for me to guess. Okay, cos x plus c. Right. Now when I say tan x dx, okay. Now I have to think of d by dx of some function which gives me tan x. And I'm going to say ln sec x. यही होता है ना आंसर? लेकिन ये कहां से आया? अचानक से एक some insights came into me that, okay, fine. So I'm not able to right now, I'm not able to think how this answer is cropping up, but I can check that whether this answer is correct or not. So कैसे check करें? How to check this? Derivative. So 1 upon sec x into sec x tan x. Okay, fine. My answer is fine. But you see, it's little like everybody cannot think this way. It's totally dependent on your insight now. Okay, fine. You were lucky enough that you were able to think that, okay, it is ln sec x. But actually, you won't hope every time. Mathematics में तो ऐसा नहीं है ना. You don't have to hope every time for the insights, right? So we'll talk about this also. Okay. So similarly, when I had to find sec x dx, what will be the answer? Log sec x or plus tan x? Plus tan x plus c. Okay, fine. So again, from where this answer came up, cropped in, we don't know. Right? It was just a share, but we can check that whether this answer is right or not. So I can see that, okay, 1 upon sec x plus tan x into sec x tan x. Chain rule, we are going to put chain rule plus. So finally, it will eventually come out to be sec x. So you see what we said in the early part, that it is easier to differentiate, but it's difficult to anti-differentiate. And now you must be having a respect for integration, that, okay, fine, it's something which is a tough nut to crack, because every time we cannot depend on insights. We are actually thinking of some answers, cooking it up, and then trying to find the right answer, right? This is the way we are doing actually. Whatever we solved till now, it was like cooking up the answers. Okay, fine, I know the differentiation of that. Okay, so cook things up. We use those two basic rules and we were trying to find the answers. Okay, we were totally depending on the insights. Clear? But one good news is that we are going to formulate it. We are going to systemize everything, and we are going to create a tools for which we will be able to solve questions, right? Now let's say I have to integrate e to the power x dx. So I'm going to guess, okay, e to the power x, because differentiation of e to the power x is e to the power x. So no problem in this, right? It was very easy to guess. What about this? How to guess this? 1 upon x. No, this is not differentiation, this is an integration. Okay, so I'm going to guess x ln x. Okay, I'm going to guess the answer as x ln x. So I can differentiate to check whether I have got the answers right or not. So when I differentiate it, I get x into 1 by x plus ln x. This is the product rule. First function into derivative of second function plus second function into derivative of first function. This is the product rule. So we got the answer 1 plus ln x. Okay, we are pretty close. We are pretty close in our guess. So difference, the derivative of a difference is difference of the derivatives, है ना? So क्या हो जाएगा? So I can say that okay, x ln x minus x plus c. Right? Now it's fine. This is how we guessed it. Right? But you don't you think that it's really getting little, every time we have to think, we have to guess, and then somewhere we are not able to find the right way to solve the questions. We have to think, we have to always depend on the idea of insights. We have to depend, right? So it's not getting mathematical anyhow. Mathematical, it's more about, okay, we are going to systemize everything. We are going to systemize, okay, if this problem comes, we are going to go this way. If this problem comes, we are going to go this way, right? So things are getting little bad, right? So should I rub this? Now let's say I have to integrate e to the power minus x square. So I'm going to make a guess, right? I'm going to make a guess. I'll say e to the power minus x square upon 2x. I'm going to make this guess, right? So I'm going to check it whether my guess is right or not. So we are going to make a product rule. Product rule लगा सकते हैं इसमें. इसको differentiate करेंगे. So I'll put 1 by 2x as constant into, if I differentiate e to the power minus x square, remains e to the power minus x square into 2x plus e to the power minus x square. I'm going to differentiate 2x to the power minus 1. So what is differentiation of 2x to the power minus 1? 2x to the power minus 1, है ना? So minus 1 into 2x to the power minus 2. So things are getting very weird, right? Very messy. See, we are not even getting close. That okay, fine, this gone minus ex square, but this thing is gone. It's getting ex square to the power 4x square. And when we are going to differentiate further, it will going to become further multiplied to the powers, right? So things are like difficult. Now, since you have already done differential calculus, can you guess this graph? Can you draw the graph of this function e to the power minus x square? What will be the graph? When I talk about e to the power minus x square, it will be a bell-shaped graph. Right? It will be a bell-shaped graph. A very important graph in statistics, in the field of statistics. Okay. So we are getting a bell-shaped graph because e to the power minus x square is a even function. Now at x is equal to 0, it becomes 1. And at x is equal to infinity, it becomes 0. It approaches 0, right? So it's something like this. Now, I have to think of capital Fx whose, right? So, I can think about the Fx part as if it will always be positive. So I can say my Fx increasing function. Can I say it? Can I say it fx is increasing function? I can also say that at x is equal to 0, slope of fx is 1. I can also say that when x approaches infinity, plus infinity, when x approaches plus infinity, my f prime x approaches 0. And when my x approaches minus infinity, then also my f prime x approaches 0. So you see that, okay, I don't know what my fx is, but I know certain things about my fx, that it is an increasing function. It has a slope 1 at x is equal to 0. It has a slope 0 at infinity, and it has a slope 0 at minus infinity. Right. Now I am going to double differentiate it. So f double x will be equal to e to the power minus x square upon minus 2x. Right. यही हो रहा है, यही होगा ना डिफरेंशिएशन. क्लियर. अब हमें ये पता चल रहा है कि things like I can guess about the function like it will be something at x is equal to 0. For positive values of x it will be negative, and for positive values of x it will be negative. This thing, double derivative. If x is positive, this thing will be positive, so the whole thing will become negative. And for x less than 0, things will become positive. So I can say about the graph, it will be something like, understood? Concave up. You understood the concavity inflection point, right? You see this is an inflection point. Now at infinity it is going this way and it is going this way. So isn't it amazing that we can think, we can sketch a rough graph, but we are not able to write that function, right? We are not able to write that function, but we are able to sketch it. So one thing you should note it down, that it is not hard but impossible. It is not hard but impossible to write the antiderivative of some functions with the functions which we have in hand, like polynomial functions, trigonometric functions. See, हम लोग अब तक सारे functions को we were able to write it, right? In our whatever functions in our hand we had, we were able to write, but this function we are not able to write. So there will be functions, some functions will be non-integrable, some functions will, even when they are integrable, we are not able to write it, right? Because we have certain functions in our hands and we are not able to write those functions with those functions. Similarly, if I throw a 20-digit prime number, you will not be able to anti-multiply it. If I throw product of two 10-digit prime numbers, you are not able to anti-multiply. Though both of them, one of them can be factorized, one of them cannot be factorized. You getting the idea? Similarly, there are functions which cannot be integrated, or there are functions which can be integrated, but it is impossible or difficult for us to write anti-differentiation of that function, so that whatever functions we have in hands, it's difficult, right? So getting the idea? Now, should I rub this? So you are able to understand that things are little, but still we are not reaching to the solution, right? अभी तक हम लोग सिर्फ देख रहे हैं, we are seeing that okay, things are a little messier, things are a little difficult, and we are depending on intuitive ideas. We are hoping for an insight every time that okay, fine, some insight comes. But we know that differentiation is easy, right? We know that differentiation is easy. So in examination also, suppose let's say if you're not able to get any insights or you're not able to get any tricks, so what you can do? You can go through options. You can hit for the best option. Okay, fine, it looks like the right option, and you can differentiate it to see that you are getting the question or not. Okay, you can do it that way also. But now we are going to develop a tool for which we are going to have a method for integrations, right? उससे पहले, before going into that, tell me, what will be the integration of this? Sine 2x minus 3 upon 2. Right? Why did you divide it by 2? Because you guessed that, okay, fine, cos 2x minus 3 is sine 2x minus 3, and when you differentiated it, you got cos 2x minus 3 along with 2. So you balanced it by dividing by 2, right? So you said the answer would be this. If I say e to the power 2x minus 3 dx, right? So if you know the antidifferentiation of fx as fx, so f of mx plus b dx becomes f of mx plus b. Clear? Right? This is how you're going to think. Now you know the chain rule. What was chain rule? What was chain rule? If I have something like y is equal to f of gx, so I can say that dy by dx will be f prime gx into g prime x. यही था ना? Now we have to do anti-thinking of this. Chain rule in reverse. What is chain rule in reverse? What is it called? I can say this, that okay, fine. If I have something like f of gx into g prime x dx, my answer would be f of gx. Can I say this? Can I say this? This is called substitution method. Thinking of chain rule in reverse. Okay, thinking of chain rule in reverse. Right. Now let's go into the assignment sheets, and we will be slowly we'll be creating our tools to how to deal with various functions जिसका हमें antiderivative निकालना है. Okay. Can we go to the assignment sheets? Okay. Initially, the basic functions like trigonometric functions, inverse trigonometric functions, and then polynomial functions, and then exponential functions, and then log functions. इनका हम लोग differentiation जानते हैं, तो उसके उल्टे सोचने की कोशिश करेंगे, ठीक है? So let's say first one is sec square 2 minus 3x dx. So what is the differentiation of tan x? So I'm going to write my answer as by, right, plus c. You know why we put plus c every time? Let's say I have fx and I have gx, and I know fx is equal to gx. The antidifferentiation is gx, and differentiation is this fx, right? So I'm going to think of a function hx is equal to fx minus gx. Now I'm going to differentiate it. H prime x. What will be it? fx minus gx is equal to 0. What does it say about hx? That it is a constant function, right? So this is how we are going to think of C. So you see the first answer is very easy. Now the second question, see, sine of 2 minus 3x upon cos square 2 minus 3x. I'm not comfortable this way. I want to put in a linear way. So I can say this as sine 2 minus tan 2 minus 3x into sec 3x dx. When we differentiated sec x, what was the answer? So I can say my answer will be by plus c, right? Similarly, I can find my answer of e to the power 2x minus 3. Similarly, okay, now sec 2 minus 3x, right? So हमने देखा था sec x का integration as log sec x plus tan x. How we arrive to that answer? देखो, we thought ऐसे sec x को देखो. अब we were knowing. Now we are going to actually apply the method of substitution. Okay. So before I apply to the method of substitution, I know something about sec function. I know something about tan function, and I know the relation between them, right? So I'm going to play a little with it, like right. I can do this. Now I see the differentiation of this is above. So can I say this as f prime x upon fx dx if my fx is sec x plus tan x? So what will be the solution of this? किस अगर मैं ln fx को differentiate करता हूं तो I get something like this by applying the chain rule and thinking of chain rule in reverse. So I can say, so my answer would be ln sec x plus tan x, and there the answer would be ln sec 2 minus 3x plus tan 2 minus 3x upon minus 3. Very good. Similarly, you see fifth question. It's like no, first ka fifth. Yeah, first. Now you see 4x plus 1 to the power minus half dx. You know how to apply? So the answer would be 4x plus 1 to the power half divided by half into, clear? Similarly, I can handle sixth part, right? Now should we go to the second part? Okay. Now you see the second questions, we have something like x minus 1 upon x plus 1. So how are we going to deal with this? X minus 1 upon x plus 1 dx. So I can write my numerator as x plus 1 minus 2. So I can say x plus 1 minus 2 upon x plus 1 dx. So finally something like dx minus 2 into dx. We can handle this. It will become x. It will become ln x plus 1 plus c, right? The second question is, how we are going to deal with it? In a similar fashion, we are going to do x square plus 1 minus 2 upon x square plus 1 dx. So it will be dx minus 2 into, where we saw this result, tan inverse x को हमने differentiate किया था, तो we got this. So x minus 2 tan inverse x. Clear? Similarly, if I have to solve x to the power 4 plus 1 upon x square plus 1. Right? How to go for this? See, we have a 2-degree thing in the denominator and 4-degree thing in a numerator. So I can easily say my quotient will be 2 degree and then some linear remainder, है ना? Some linear remainder. तो कुछ वैसा करने की भी कोशिश कर सकते हैं. अदरवाइज हम एक और चीज क्या कर सकते हैं? प्लस 2x माइनस 2x कर सकते हैं. उससे क्या होगा? That will think will become x square plus 1 का स्क्वायर. तो एक कट जाएगा और दूसरा बच जाएगा something like I can say plus 2x minus 2x upon x square plus 1. One thing you know, divide it. The quotient will be the 2-degree thing. Polynomial, you know how to integrate polynomial. And then you get something like linear upon quadratic form. So we are going to discuss that also. So you see, thing will be something like x square plus 1 ka square minus 2x upon x square plus 1 dx. So we can say that x square plus 1 dx minus 2x dx upon x square plus 1. Again we got, if it is, this is my fx, the above thing becomes f prime x. So f prime x upon fx becomes lfx. So I can say x square plus 1 dx, ये तो easy हो जाएगा, x cube by 3 plus x minus ln x square plus 1 plus c. Clear? Similarly, okay, now I have got something like x to the power 7 upon x plus 1. How to solve? जब भी हमें पास odd power हो higher degrees में और नीचे x plus 1 हो तो हम इसको factorize कर सकते हैं क्या? Plus 1 minus 1 करके? नहीं. Tell me. X plus 1 is x plus 1, right? X cube plus 1 is x plus 1 into x5 plus 1 is equal to ये बात पता था? x to the power 7 plus 1 क्या होगा? Clear? So I can now handle it. I'm going to put x plus 1 minus 1. तब odd power से समझ में आ रहा है ना कैसे करना है? So it will be like x to the power 7 plus 1 upon x plus 1 minus ये dx रहने दो यहाँ पे upon dx upon x plus 1. You can solve this and you can solve this now. That will become a 6-degree polynomial and you know how to handle polynomial, right? Done. Now let's go for 5th question. The 5th question is x cube upon x plus 1 ka whole square. So you have a cubic function above and a quadratic function below. So how to deal with it? Now you see x plus 1. So again I can add plus 1 minus 1. So I'll get something like so it will be something like you can easily handle this. This will become x plus 1 to the power minus 2 and thing will become x plus 1 to the power minus 2 plus 1 upon minus 2 plus 1. Coefficient of x is 1, so no problem with that. Plus c, right? ये तो हो जाएगा. What is x cube plus 1? I know that is x plus 1, so I can say this thing will become x square minus x plus 1 upon x plus 1. We have already solved this. अब how to handle this? Divide करते हैं. तो I will get what? x plus 1 से अगर मैं divide करता हूं, minus 2x plus 1, and I'm going to put it minus 2. So it will be minus 2x plus 2. Sorry, minus 2. है ना? So I'm going to get 3. So I get something like x minus 2 dx plus 3 upon x plus 1 dx. Easy to handle. है ना? Clear? Now how to solve C part, sixth part? ax plus b upon cx plus d. हम लोग हमेशा फैक्टर करके कट डाउन कर रहे हैं whatever things we have. So I can write my ax plus b as a integral, as a multiple of some number to this denominator plus some constant, क्योंकि ये linear है, it will also be linear upon linear. So I'm going to write this way like, okay, fine. I'm going to put this way as a by c into cx plus d, right? So I get my ax, but instead of b, I got something like ad by c, right? So I'm going to subtract it. And what is the extra constant term we have? Plus b upon cx plus d. So I'm going to split it. So I'll get something like a by c dx, right? It will cut down, and something like minus ad by c plus b and we get something like plus b minus ad by c into dx by cx plus d, right? Clear? So this is how we are going to find the answer. So what will be the solution of this? ln cx plus d about c and then we are going to handle it everything, right? Clear? Not clear? From where? Okay, till here what we were doing, we had a linear term in denominator and we had a linear term in numerator. So I wanted a quotient first of all, a numerical number. So I say I break my ax plus b as a sum number into cx plus d plus some number, right? So I get cancel this, I get a by c dx, right? Now things are like minus ad plus c by b, that is b minus ad by c upon cx plus d. I can remove my constant out. So it will be dx upon cx plus d. So what will be the solution of this? ln cx plus d upon c. That's it. The constant is out. Okay? Clear? Now when we are doing the substitution method, the choice becomes that which function should we substitute. तो हमेशा हमें choice उसमें रखना चाहिए जिसका हम लोग easily du part, let's say I am calling it a u substitution. So if I am choosing a function u, then I can easily grab the du in that. I can easily recognize the du in that. u और du को recognize करना ही substitution method का challenging part है. Nothing उससे ज़्यादा कुछ भी challenging नहीं है. Otherwise, you know, it's just a reverse of chain rule, right? So when I see this function sin inverse x dx upon under root 1 minus x square, I feel very uncomfortable when I see sin inverse x. It's very difficult to integrate. और differentiate करने में भी हम लोगों ने थोड़ा सा तंग हुए थे, परेशान हुए थे थोड़ा सा, है ना? So, but I know the differentiation of sine inverse x is this. So it's very easy peasy question. Like I can substitute u as sine inverse x. So du becomes dx upon. So I can see, okay, it is u du. What is u du? U square by 2 plus c. And what is u? Sine inverse x square by 2 plus c. Clear? So what is the challenging part in substitution method? Recognize u और recognize करने के लिए we can easily see कि किसका du दिख रहा है ना? Now see the second question is now again they are talking about sec and tan. So I can easily say the differentiation of sec x is sec x tan x. So I can say sec cube x sec x tan x dx. So I can recognize this is my u. So it will be something like u cube du, right? Because sec x is u, so du is becomes sec x tan x dx, right? So the answer would be u to the power 4 by 4 plus c. And what is u? So sec to the power 4x by 4 plus c. Clear? Easy question. Now similarly see sine to the power 5x cos x. Now you see cos is alone and you see on the left side sine. So cos x dx. So sine x becomes my u. So u to the power 5 into du, that becomes u to the power 6 by 6 plus c. And what is u? Sine x. So answer becomes sine to the power 6x sine to the power sine x to the power 6 upon 6 plus c, right? Okay. Now see, we have to evaluate this x cube upon 1 plus 4 x to the power 4. So it's now very easy to grab du, right? Because I can see 1 plus x4 as one function. And what is the differentiation of 1 plus x4? 4x cube. So constant is there. Constant is the issue. So I can multiply that thing by 4 and divide by 4. So I can say 1 by 4 into 4x cube upon 1 plus x to the power 4 dx. So I can say 1 by 4 du by u. So I can say 1 by 4 ln u. So I can plus c. So I can say 1 by 4 ln 1 plus x to the power 4 plus c. Clear? Easy question. Now if you see second part is e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. So I see the denominator and I see the derivative part as just the numerator. So I can say easily that my answer is ln e to the power x plus e to the power minus x. What about third? See, if second question gives me a hint to the third questions. Otherwise, it would have been a little difficult to think. The second question gives me a little hint about the third question. Like, see, we saw e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. Now, in the second question, we have e to the power x plus 1 upon e to the power x minus 1. Right? So, are you able to think कि मैं क्या बोलना चाह रहा हूँ? क्या? I want this thing should have anyhow मैं उसको e to the power minus x वाली कहानी ले आऊँ. उससे क्या हो जाएगा? फिर इधर 1 आ जाएगा. I don't want to disturb also this also. If I divide numerator and denominator by e to the power x by 2, तो क्या बन जाएगा? Plus e to the power minus x by 2 over e to the power. So we are getting the same figure. We are getting the same figure. See, integration won't become totally mechanical thing. Integration needs little cooking up, little insights, little cooking up, right? So I see e to the power x plus 1 upon e to the power x minus 1 dx. The previous experience says that anyhow, if I get this, things will be fine, right? So what I did, I tried to divide it by e to the power x by 2, which will make this as right. Now, if I take this as u, what is u? E to the power x by 2 minus e to the power minus x by 2. So what will be my du? Half e to the power x by 2 plus half e to the power minus x by 2 dx. So half is missing, right? So I can replace thing by 2 du. So I can say 2 du by u. So I can say, what is ln u? Clear? Huh? Done. So you see the idea. Now what about question number 4? I got something like dx upon a plus b ex, e to the power x. So if I'm going to grab this thing as my u, I'm not getting my du, right? I'm not getting my du. So कुछ ऐसा ही यहाँ पे भी सोचते हैं. Can I multiply numerator and denominator by e to the power minus x? So what I get? E to the power minus x dx upon a e to the power minus x plus b. Now things I can easily grab, right? What is it? I can grab this as u. If I grab this as u, this will become du. So I can say 1 by a du by u. So I can say 1 by a ln u plus c. And what is ln u? This thing. Clear? तो आप समझ में आ रहा है e to the power x की कहानी में क्या करना है जब भी न्यूमरेटर डिनोमिनेटर में हो. तीनों का पैटर्न देखो, है ना? सो सब्स्टिट्यूशन में सबसे इसमें तुम्हें थोड़ा सा मैनिपुलेशन करना पड़ा to get a safe u and safe du, right? Now similarly, look for question number 5. Again I am getting some function and then constant and then same function upon minus. तो क्या करें? हाँ, can I get everything in my sin cos form? So क्या हो जाएगा? Is it the same thing? पक्का? So I can say ln sin x minus cos x plus c. जब भी ln लिखो मोर डाल दो. क्यों? ln नेगेटिव वैल्यूज के लिए नहीं होता है ना. Okay. Now let's say question number 6. Now if I see that sec x dx upon ln sec x dx upon ln sec x plus tan x. So I don't know exactly what will be the differentiation, but can I check? There's no wrong in checking it. So let's say if I say u is my ln sec x plus tan x, my du becomes 1 by और we already knew कि क्या कहते हैं sec x का ये होता है, तो इसका एंटी डिफरेंशिएशन ऑब्वियसली sec x होगा, तो we'll get something like so what will be the answer? Okay, du is sec x dx, so I can say du by u, so it will be plus c, and what is u? ln of ln sec x plus c. Clear? Understood? Now let's say think of question number 7. We see x square minus 1 upon x into x square plus 1. We see something like cubic, we are being tempted, but the numerator is 2 degree and denominator is 3 degree. So we are not going to divide on something like, है ना? Okay, denominator cubic में है, लेकिन we are getting thing like x square minus 1 and x इस form में जब भी हो, whenever you see x square plus 1 form or x square minus 1 form, always try to do this method. X square minus 1 upon x into x square plus 1 dx. ठीक है? If I divide my numerator by x square, so I have to divide my denominator also by x square. So what is the result? 1 minus 1 by x square dx upon x plus 1 by x. We have a relation, right? So whenever we see x square plus 1 and x square minus 1 and नीचे x plus 1 by x का फॉर्म बन रहा है, या x square plus 1 by x square का फॉर्म बन रहा है, या x to the power 4 plus 1 by x to the power, समझ में आ रहा है ना? We can easily write the function in x plus 1 by x form. So we'll always think of this. अगर x square plus 1 है या x square minus 1 है, तो अब मैं इसको कह सकता हूँ u, so ऊपर क्या हो गया? du by u ln u plus c. So what will be the answer? Clear? अब देखो उसमें क्या है, 8th क्वेश्चन में क्या है? dx upon x plus root x, right? क्या कॉमन बाहर निकालेंगे? उससे क्या हो जाएगा? We get something like root x plus 1. So we are going to think of root x plus 1 as u. Will I get something in the form of that? Some quotient will, some constant will also come. Let's try this. See, I have dx upon x plus root x. So I am going to take this thing out. Right, I'm going to grab this as u. So u becomes root x plus 1. So du becomes 1 by 2 root x dx. So 1 by root x dx becomes 2 du. So I can say 2 du by u. So I can say 2 ln u and 2 ln root x plus, right? Now, इसमें देखो क्या कहते हैं, which one should we grab as u? Tan inverse x square. And if I differentiate tan inverse x square, what will get? D. क्या? 2x upon, very good, into dx. So we can easily see things, right? So I can say the question is x dx upon x to the power 4 plus 1 tan inverse x square. So I'm going to treat tan inverse x square as u. So when I say u is tan inverse x square, my du becomes 1 upon 1 plus x square ka square, that is x to the 4. I'm going to do the chain rule. So 2 is missing, right? So I can write this as du by 2. So I can say half du by u. So half ln u plus c, and what is half ln u is tan inverse x square plus c. Clear? Now this one, which one should we choose as u? Log x. So if I differentiate log x, it will become 1 upon log x. Let's do it. So I see something like dx upon, so you are getting a flavor key which one needs to be substituted, right? है ना? So you see log, मैंने u को बना दिया log x. So my du will become 1 by log x into 1 by x. So I can see my ex du part also and u part also. So it will be du by u, that is log u, and that will become log of log x. So answer will be clear. Now this one, 11th part. Sine 2x upon 1 plus sine square x dx. So I'm going to take 1 plus sine square x as u. So this will become 2 sine x cos x. What is 2 sine x cos x? Sine 2x. So I can easily say that ln 1 plus sine square x plus c. Now 12th part, I have the denominator as e to the power x plus x to the power e. If I'm going to grab e to the power x plus x to the power e as u, then what will be my du? E to the power x plus e into x to the power e minus 1. So I can see easily that e has been removed from my numerator. है ना? E has been removed from my numerator. So I can do little changes in it. I can say e to the power x by e plus x e to the power minus 1 upon e to the power x plus x e to the power x. यही है. So मैं इसको ठीक कर सकता हूँ. हो गया सॉल्व, राइट? हो गया ना? This is your polynomial thing, not polynomial thing, but x algebraic thing, जिसमें x, what we said that कोई भी power हो, it should not be equal to -1, else all the numbers are accepted, all real numbers are accepted. ठीक है? तो e into x to the power e minus 1. Clear? Next sheet. Okay, we are very comfortable when I see my linear sin x, है ना? But we are not very comfortable when it comes to sine square x. But we have already studied trigonometry chapter in class 11th, and we know how to convert a square sine into a linear sine or cos. So how to convert sine square x? 1 minus, I can say sin square x is nothing but 1 minus cos 2x by 2 dx. I can handle this. I can easily handle this. Similarly, now what about sine cube? Do we have to do anything? It's fine. Simple sine cube को क्या करना होगा? Sin square x. फिर क्या करना होगा? और क्या करना होगा? Cos x को u मान लो. तो it will be 1 minus u square and this will be minus du. Minus बाहर निकाल दो. Clear? Similarly, think of sin to the power 4x. कैसे करें sin to the power 4x? करो ये क्वेश्चन. Okay. So are we done with sin to the power 4x? How to go for it? I have to make it sin square x square. So I'll just help you. So I'm going to write sin to the power 4x as sin square x to cos square dx. Right? And I can convert my sin square x as 1 minus cos 2x by 2 ka whole square dx, right? I can expand it. I can put my 1 by 4 out. I can say 1 plus cos square 2x minus 2 cos 2x. I can handle 1 by 4 dx. I can easily handle minus 2 cos 2x dx. And how to handle cos square 2x dx? 1 plus cos. So again, we got the linear term. So we can easily handle now. So it will be something like x by 4 minus 2 by 4 cos 2x dx किसका होगा? Sin 2x by 2 plus 1 by 4 into 1 plus cos 4x by 2 dx. Right? So we can easily handle this. It will be 1 by 8x plus 1 by 8 cos 4x dx. That will be sin 4x by 4. Clear? What about the fourth part? Sin to the power 4x into cos to the power 4x. Can I multiply my thing to the power 4 upon 2 to the power 4? Why? I'm going to convert that as sin to the power 4, sin 2x to the power 4. And you know how to handle sin to the power 4x. So you can easily handle sin 2x to the power 4. The same solution, right? But यहाँ पे x बन चुका है 2x, तो ये बन जाएगा 4x, 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 ये बन जाएगा 8x, and you can handle the constants, right? So you can easily handle this type of questions. Whenever you see sine square, sine cube, sine to the power 4, or sine to the power 4 into cos to the power 4. Okay, if I would have given the question sine to the power 4x into cos cube x, तब क्या करते? You see odd thing, cos के साथ odd thing आ गया है, तो odd निकाल दो ना, cos x dx कर दो, and make rest of the thing as u, and make another thing as du. You have to recognize u or du. The moment you recognize u or du, things are fine, things are done. Right? Now should we go to sixth question? Okay, the sixth question is dx upon 1 plus sin x. How to deal with it? क्या किया जाए? Tan 2x. Okay, you think that whenever you see a linear combination of, we'll come to that part also. In 8th part, we'll discuss that. But we have another method also. When we see dx upon 1 plus sin x, multiply and divide by 1 minus sin x. So I'll get something like upon 1 minus sin square x, that is, now things will become like sec square x dx minus sin x dx upon cos square x. So you can easily solve this, you can easily solve this, right? We'll come to that thing which you mentioned, right? So similarly, dx upon 1 plus cos x क्या होगा? I can write this as 1 minus cos x upon sin square x. Now I know how to integrate cosec square x. How to integrate cosec square x? Minus cot x, right? And how to integrate minus cos x dx upon, you can handle that, right? Now let's go to 7th question. I see the product of sine, then in the next question I see product of sine, cos. Third part we have already done. How to deal the third part? है ना, sin square x, cos square x. So let's think of first. आपने trigonometry में पढ़ा होगा how to handle sin A into sin B, and how to handle sin A cos B, how to handle cos A cos B, right? How to handle sin 2x cos sin 3x? First, I'm going to multiply by 2 and divide by 2. So it will be something like half 2 sin 2x sin 3x plus dx into dx. Now I see these sin A sin B term in cos A plus B and in cos A minus B. In cos A plus B it comes with a minus sign, and in A minus B it comes with a plus sign, and I want my thing in a plus sign. So I'm going to say this as half into cos A minus B minus cos A plus B. So what will be the cos A minus B क्या हो जाएगा? 3x minus 2 is x minus cos A कुछ भी ले सकते हो, 2 भी ले सकते हो, 3 भी ले सकते हो, क्योंकि cos माइनस अगर तुम एक माइनस में आता तो क्या फर्क पड़ता? कोई फर्क ही नहीं पड़ता. Cos is an even function, right? Now you can handle this. Similarly, if you see the second question, sin 2x into cos 4x into cos 5x dx. है ना? Choose any two, choose. You can choose these two. है ना? If you choose this two, it will be cos 9x plus cos x divided by 2. और फिर उसके बाद फिर it will split into sin A cos B and another sin A cos B. है ना? So how to handle sin A cos B? You know, sin A plus B plus sin A minus B. Clear? Be very particular, very careful about choosing A and B, and see कहाँ पे sin. जैसे cos में we were a little casual because cos को फर्क नहीं पड़ता है plus minus से, but sin को फर्क पड़ता है. So you have to be very careful, right? Now the third part is simply I'm going to multiply by 4 and divide by 4. So it will become sin square 2x. And I know how to handle sin square x. So I can easily handle sine square 2x. Clear? Now, whenever see the 8th question, now we will come to that part. Whenever we see that I have something dx in the above part, and in the lower we have got a linear combination of sine and cos. Whenever we see the linear combination of sine and cos, we are going to think of this way. What is the differentiation of tan x? sec square x, है ना? और आप पहले याद करना, आप लोग क्लास 11th में you must have done this, that sin x is 2 sin x by 2 cos x by 2. Clear? I want my sin x to represent everything in tan form, in a half tan angle form, है ना? So I'm going to divide by cos square x by 2 into sec square x by 2. Because I know a very close relation between sec and tan. I know 1 plus tan square x is sec square x. ठीक है? And now I can, नीचे हमने क्या किया, divide किया 1 से तो divide कर ही रहे हैं, कुछ फर्क नहीं पड़ता है. So I can cut down this and I can cut down this. So what is my numerator? 2 tan x by 2 over 1 plus, ये रिलेशन आपको पता है sin x में. Similarly हमने cos x का भी रिलेशन निकाला था. Cos x is nothing but cos square x minus, so I'm going to multiply and divide by cos square x into sec square x. So that above thing will become 1 minus, है ना, 1 minus tan square x by 2 upon clear. So I get something like sin x can be written as 2 tan half angle plus 1 plus tan square half angle, and cos can be written as 1 minus tan square half angle plus 1 upon. तो ये कर क्यों रहे हैं? Because we are getting 1 plus tan square half angle. And what is 1 plus tan square half angle? और denominator में ये जब नीचे आ जाएगा, it will reverse to the numerator. I have got my this part in the form of tan, and in numerator I get the form of sec square x dx. So now I can do easily substitution, है ना? देखो कैसे करेंगे. So I'll say that my dx upon a into 2 tan x by 2 upon 1 plus tan square x by 2 plus b into 1 minus tan square x by 2 upon 1 plus, ठीक है? So this thing will go up, so it will become sec square x by 2 dx upon 2a tan x by 2 plus b minus b tan square x by 2, and I'm going to put tan x by 2 as t. So if I put tan x by 2 as t, I'll get half sec square x by 2 dx as dt. So I can put as 2 dt upon 2at plus b minus bt square. So I got something like, so problem, right? So okay, so that would be little problematic, है ना? The 2a plus b minus 2at plus b minus bt square. So we see a quadratic form in the denominator form. Okay, clear? So we'll be dealing with it, how to handle when we have dx upon quadratic form. Okay, so right now you can leave it till here. When we'll be going to question number 12, then we'll be handling how we'll learn how to handle these type of problems. Okay. Now if you see question number 9th, I have again e to the power x into x plus 1 cos x e to the power x dx. Right. So how to go for it? I'm going to grab my u. That thing will become cos x e to the power x as my u. I'll just guess it. And then when I differentiate it, I'm going to grab x e to the power x as my u. When I'm going to grab x e to the power x as u, what will be my du? E to the power x into x plus 1 dx. So I can say the thing has become cos t into dt. When I have to integrate cos t into dt, sin t, and what was my t? X ex. So answer will be sin x ex plus c. Do I have to solve it, or you understood? Okay. So similar thing. Whenever you see some complex thing, you first of all you should have a little idea which one will be differentiate to give me that. So you should be able to recognize du. You should be able to grab that du thing. Okay. Now if you see question number 10, first part, it is like x squared dx upon 1 plus x to the power 6. Okay. I know x to the power 6 as a multiple of x cube. X cube ka square is x to the power 6. Now if you see x cube as if I am going to grab x cube as u, what will be my du? 3x squared dx. So I have x squared dx above, right? I have x squared dx, so I can write 1 by 3 into 3x squared dx. Okay. So I can say that 3x squared dx upon 1 plus x cubed square into 1 by 3. I can write this, and I'm going to put x cube as u. So it will be something like 1 by 3 du upon 1 plus u square. You know how to handle this? Tan inverse u. So 1 by 3. And what is u? Right. This is the way we are going to handle. So we have just solved how to solve x square plus 1 form. But we haven't done all the 3 quadratic form. So we'll be going to, when we'll be in 12th part, we'll be able to handle how to solve dx upon quadratic. Now if you see the second question, dx upon x plus cube root of x. So I can grab my x cube root out. So what will I get inside? X to the power 2 by 3 plus 1. Last time what we did when we had 1 plus root x, we removed root x out. Similarly, we are going to remove x to the power 1 by 3 as dx upon x plus x to the power 1 by 3. This is the question. So I am going to remove x to the power 1 by 3 out. So it will be 1 by x to the power 1 by 3, x to the power 2 by 3 plus 1 dx. Now, of course, I have to choose u. I'm going to choose x to the power 2 by 3 plus 1 as u. So what will be my dx? 2 by 3, x to the power minus 1 by 3 dx is equal to du. So I can say as 3 by 2 du. Clear? So now I can do the substitution, that this part is my du, 3 by 2 du, and this is my u. So answer is, and what is u? X to the power 2 by 3 plus 1, right? I got something like x square upon under root 1 plus x dx. Which one should I choose as u? Can I put 1 plus x as my u square? Can I say my 1 plus x as u square? So what will be my dx? 2u du. So, and what will be my x square? U square minus 1 ka square. So I'll get the whole thing in polynomial form. and we can easily handle polynomial form. So we'll get something like u square minus 1 ka square upon u into 2u du. I can easily handle now. My answer will come in a polynomial form of u, and how to replace u? Just by under root 1 plus x. Clear? Good. Now similarly, question number 4. Question number 4 talks about 8 to the power x into 8 to the power tan inverse 8 to the power x upon 8 to the power 2x plus 1 dx. So this is giving us a hint. 8 to the power 2x plus 1 is giving us a hint because tan inverse here. So it is giving us a hint key which one should we choose as u. So I'm going to choose tan inverse 8 to the power x as u. When I choose tan inverse 8 to the power x as u, I'm going to differentiate it. So it will be 1 upon 1 plus a to x 8 to the power x ln a is equal to du dx. Clear? So ln a is required. So I can divide and multiply by ln a. So I can say that 1 by ln a, this thing has become du into 8 to the power u du. है ना? Okay, now e to the power x dx तो हमें पता था. We knew how to solve e to the power x dx. How to solve 8 to the power x dx? Why? Because when we differentiate 8 to the power x, we get ln a as a multiple. So we have to balance it. So we'll be divided by 2. So I can say my answer as 1 by ln a into 8 to the power u upon ln a plus c. I can replace now u as a to the power tan inverse a to the power x and ln a square. Right? Clear? Okay. Now, since question number 5, we have root sine theta plus cos cube theta into d theta. So which one we should choose as d theta, as a u, cos or sine? I feel sine. I feel sine to be chosen as u, because I can write my cos cube theta as cos square theta into cos theta, and I can write my cos square theta as 1 minus sine square theta. So I have problem with root sine theta, right? So I cannot choose cos theta as u, because then my problem is not solved, because I want to get du part. Only sine theta helps me in getting the du part. So I'll say cos theta d theta as du, and that other thing will become root u into 1 minus u square du. You can easily solve this. Break it. Enough. You'll be able to handle it. Now, question number 6. How to go for it? Now, if you see question number 6, some of the students are non-Hindi background or what? Okay. So we have something like root x dx into under root 1 minus x cube. Now here actually the real test is done to choose u. You see root x, you see 1 minus x cube to the power half. So somewhere you see x to the power 3 by 2. When you differentiate x to the power 3 by 2, you get something this. So I'm going to substitute as x to the power 3 by 2 as u. So I'm going to say x to the power 3 by 2 as u. So this will become 3 by 2 x half dx as du. So you know how to handle root x dx. So things will become like 2 by 3 du. Is it a known form? What is it? Sine inverse u. So it will be, and what is u? So you got the answer, right? So whenever you see, don't panic. The thing is that you should not panic. You should see. Let's say even if you are not able to think of x to the power 3 by 2, think of 1 minus x cube as u. You're not able to find it, right? So what should the next thinking should come? Right? This way you can think of. Now, question number 11, as we see, lots of tans and lots of sec. Now you see tan square x dx. How to handle tan square x dx? How to handle? To convert that thing into sec square x minus 1. And that will be very easy to handle, right? Okay, and how to handle tan square x dx? Sorry, tan cube x dx? Again, I am going to break tan cube x as tan square x into tan x. And I'm going to break tan square x as sec square x minus 1. I can easily handle tan x dx, and I can easily handle sec square x tan x, because sec x bahar nikal jayega and sec x tan x dx will become du part. So u into du part, and we know how to handle tan x dx, that is log sec x, right? Good. So you know how to handle tan square x. Now we know how to handle tan cube x. Now how to handle tan to the power 4x? In tan square x into tan square x. That will make it tan square x into sec square x minus 1. So I can say tan to the power 4x is nothing but tan square x into tan square x dx, which is nothing but tan square x into sec square x minus 1. So I can easily say that right. I can handle this. Can I handle this? I can handle this. इसे कैसे handle करेंगे? Tan x into उससे क्या होगा? Huh? I'm going to take tan x as t. So it will become t square dt. That will be t cube by 3. Clear? And you know how to handle tan square x, because that is nothing but sec square x minus 1, and sec square dx is tan x, and minus dx is x. Good. Now, how to handle sec to the power 4x? Similarly, the way we handle tan to the power 4x. है ना? Sec to the power 4x can be written as sec square x into sec square x into dx. Now I am going to write this as I'm going to grab this as u. So 1 plus u squared du. So I can easily handle that u plus u cube by 3. And okay. You know how to handle this? Question number 5. Sine cube x into cos square x. Sorry, we have okay. Whenever you see whichever has got the odd power, whichever has got the odd power, that will be integrating as a du part, right? So I am going to make this as sine square x cos to the power 4x into sine x dx. So I'm going to put cos x as u, and then my thing will become a polynomial thing, and I can easily handle that, right? And when I see sine to the power 5x dx, I'm going to, it's very easy, right? I can say sine to the power 4x into sine x, and I can say 1 minus sine square x square, 1 minus cos square x square. So I can easily write a polynomial thing, and a polynomial thing is easy to integrate, right? Now, till 11th, we were like fine, everything was good, substitution was fine, right? Now, there are basically three types of forms which we have to keep in mind, which we have to remember. But instead of just mugging it up, we will first derive it. And when we'll derive it, we'll be able to write it. Whenever, even in the examination, if it slips off, we can easily derive it, right? Now, we'll be seeing three types of cases, like dx upon quadratic, dx upon under root quadratic, or under root quadratic into dx. Okay, these will comprise of total 9 formulas. So these integration formulas should be kept in mind, but moreover, it should, rather than keeping in mind, you should be able to derive in 5 to 10 seconds. It's not difficult to derive. I'll show you how. So what I wrote, derive and remember. First of all, it's very easy. A square plus x square. We have been seeing tan inverse x ka. So we are going to write dx upon x square plus a square, right? I want a square to chop off, get out, right? So I'm going to say that 1 upon a square dx upon 1 plus x square by a square. Now I'm going to put x by a as t. So I can say 1 by a square dx will be nothing but a dt. A dt upon 1 plus t square. So I can say 1 by a tan inverse t plus c. Notice t. It was very easy to remember and very easy to derive, right? Sometimes when you are mugging up, confusion comes with the constant is there or not. Those type of things should not eat your head. That should be like, okay, fine, I forgot. Sometimes I also forgot. So you can take a piece of paper and find out. It will hardly take 5 to 10 seconds since you know how to drive through it. Now let's say I have to, so dx upon a square x plus x square is fine. It's 1 up by a tan inverse x by a, right? Now the second thing is dx upon x square minus a square. Again, I am not fine with a. So I'm going to take it out. So I'm going to say dx upon x square by a square minus 1. Again, I'm going to put x by a as t. T as x by a. So I'm going to put that as 1 by a square a dt upon t square minus 1. So I'm going to write 1 by a dt upon t square minus 1. Since I know t square minus 1 can be written as half 2a into t plus 1 minus t minus 1 upon t plus 1 into t minus 1 dt. Right? So it means I can write 1 by 2a as dt by t minus 1 minus 1 by 2a dt by t plus 1, which I can write as 1 by 2a ln t minus 1 minus ln, and you know ln a minus ln b is ln a by b. So I can say 1 by 2a ln t minus 1 upon t plus 1 plus c. And how to handle this? T can be written as x by a. So I can write x minus a, x plus a plus c. Okay? So we can easily handle dx upon x square minus a square. Confusion can, when mugging it up, when you are mugging it up, confusion can come crops that whether x minus a is up or x plus a is up. So you know how to handle that. Okay. Now I have to find dx upon a square minus x square now. Do I really have to derive it? Or just a minus sign would do it? Just a minus sign there would do it. Just a minus sign would do it. And when there is minus sign, what will be? It will reverse. Clear? We can handle this also. So these three is fine. Whenever we see a quadratic expression in the denominator, we have three cases. We have three cases: x square plus a square case, or x square minus a square case, or a square minus x square case. That is the idea, right? So now we can easily handle fourth question. We just have to recognize which one is that. So we have to make a perfect square. So whenever we see dx upon quadratic form, we have to convert our answer into perfect square form. So I'm going to write dx upon x square plus x as x square plus 2 into half into x plus 1 by 4 minus 1 by 4 plus 1. Right? So I can write dx upon x plus half k square plus root 3 by 2 k square. Clear? So this is my dx upon x square plus a square form. And how to handle dx upon x square plus a square form? 1 by a tan inverse x by a. Now the challenge here is, what is a and what is x? What is a? Root 3 by 2. So 1 by a will be tan inverse. What is x here? X plus half. And what is a? So this will be your answer, plus c, of course. Okay? Similarly, I'm not comfortable when I see my minus thing with this. Okay, so what I do, I'll put minus 2 out. I'll take minus 2 out. This will become x square plus 2x minus 1. And I can write my x square plus 2x plus 1 minus 2. And that will become x plus 1 ka whole square minus root 2 ka square. And you know dx upon x square minus a square, how to handle that? Clear? Similarly, when I see sixth part, dx upon x square plus 6x plus 9. So I'm going to write 9 minus 8. X square plus 6x plus 9 minus 8. So that will become x plus 3k square. So it will become x square minus a square. I know how to handle x. 1 by 2a ln x minus a upon x plus a. X will be x plus 3 and a will be 2 root 2. Clear? Ye dhyan rakhna, 2 root 2. Not like in this question, like it is 3 by 4 which turned out to be. And the most common mistake which we do is write a as 3 by 4. You have to make it as root 3 by 2 k square. So you have to be very careful with that. Okay. Next page. So till here you are fine? Good. So you are getting the idea that, okay, fine, initially it looked very difficult, but now things are getting systematic, more systematic. Still some of the insights are needed. It's not very straightforward like the differentiation part, but still it's very easy, right? Now, derive and remember dx upon root quadratic. So how to derive this dx upon? The same fashion we are going to derive, the way we did last. So I'm going to write this as dx upon x square by a square plus 1. I'm going to take 1 by a out. Right? Everybody understand why I took out 1 by a? Hai na? The same way I'm going to put, I'm not comfortable with x by a, so I'm going to put x by a as t. So I'm going to write 1 by a dx into under root 1 plus t square. This is gone. So I got something like dx upon under root 1 plus t square. Okay. Now, since I got this thing, it is 1 plus t square form. So what substitution we should put? That things will be fine. T should be equal to, if I put t is equal to tan x, what will be the thing? Sec square x dx, and the denominator will be? Okay, good. So it will be something like, I'm putting t as tan theta. I'm putting t as tan theta. So it will be sec square theta d theta upon sec theta, right? And I can know how to handle sec theta d theta. What is the sec theta d theta integration? ln sec theta. Okay. Since we know tan theta is nothing but x by a. So I can say that ln sec theta will be equal to under root 1 plus x square by a square, and tan theta will be equal to x by a. So I can say that ln a square plus x by a plus c. Now you see ln a by b, what is it? Ln a minus ln b. So I can write this as ln under root a square plus x minus ln a plus c. Does it have any meaning, minus ln a plus c? It is a constant, so I can remove this. Clear? So what is the general formula for dx upon under root x square plus a square? It is ln x plus under root a square plus x square plus c. Okay. You don't have to, you know how to derive it, and you can remember it. Okay. You don't have to derive for x square minus a square. Why? A square is just a constant, right? Plus a square, right? It was just a constant. So I can treat a square as a constant. So I can treat this part as a constant. It was actually, I was deriving x square plus c, if you see this way, right? So I can write my dx upon under root x square minus a square. I'll just replace wherever I see plus a square by minus a square. So I can say my answer would be ln under root x square plus x. Got it or not got it? Understood? Clear? Now x square under root x square plus a square is clear. Under root x square minus a square is clear. Now we should go for under root a square minus x square. How to deal with it? What is the answer? Sine inverse x by a. Okay. You know how to derive it? Similar fashion, right? 1 by a would be out. 1 by a would be out, and it will be dx upon under root 1 minus x square by a square. I'm going to put t as x by a. So it will be 1 by a dt upon under root 1 minus t square. A gone. This will become sine inverse t plus c. So answer is. So you know how to handle this type of questions, right? So you saw dx upon x square plus a square. You saw dx upon a square minus x square. You saw dx upon, clear. So all the three are done. So the whenever you see under root quadratic part, you are going to split in any of the three, whichever you feel that it is the right thing. Now let's say the fourth question, it's like dx upon under root minus x square minus bx plus c. So definitely it is a square minus x square form. Okay, so the challenging part would be just to resolve it into a perfect square. Let's do it. The question is dx upon under root 1 minus x square. This is the question, right? So I'm going to handle this as dx upon under root 1 minus x square plus x. So I'm going to write this as dx upon under root 1 minus x square plus 2 into half into x plus 1 by 4. So minus 1 by 4 should be compensated by plus 1 by 4. So I can write dx upon under root 5 by 4 minus x plus half k square. So this is basically root 5 by 2 k square. And what is dx upon a square minus a square? Under root sine inverse x by a. So I can say that sine inverse x plus half upon root 5 by 2 plus c. Clear? Now, similarly, we can handle dx upon 2x square plus 6. I'm going to take root 2 out. So it will be x square plus 3x plus 1. And how to handle x square plus 3x plus 1? 2 into 3 by 2. That will finally turn out to be dx upon under root x square plus a square. You know how to handle under root x square plus a square. Similarly, sixth question is dx upon under root x minus 4 into x minus 8. Basically, it has a root. So it can easily be written as x square minus a square form. It can easily be written in x square minus a square form. So I can easily write in x square minus a square form. We cannot write it as a square minus x square form. Why? Because we have a positive coefficient of x square. Seventh question is very easy. How to deal with it? I'm just going to put tan x as t. So the thing will be dt upon root 9 plus t square. That is a square plus x square. That is 3 square plus t square. And you know how to handle x square under root x square plus a square, right? Eighth part. I have a quadratic under root term in the denominator, but in numerator I have got a linear term. So how to deal with it? Any thought process? How do they deal with it? See, when I see x square plus 4x plus 1, this thing is with under root thing, right? And I have got a linear term in my numerator. What is the differentiation part of this? That will be a linear term. So I can easily any day that thing into a constant into the differentiation of this plus some constant. So I can write what is x square plus 4x plus 1. Differentiation part would be 2x plus 2. So I want anyway 3 by 2 into 2x plus 2. So it will become 3x plus 3 and but the 3x plus 3. Okay. But the numerator we have 3x plus 1. Okay, sorry. 2x plus 4. So I can any day write this thing as 3x plus this will become 6. But we have 1. So how to handle this? Minus 5 upon under root x square plus 4x plus 1. Now I can remove this 2. I can easily solve this part by substitution, and I can easily solve this part by formula. Clear? So whenever you see under root quadratic part and a linear part above, so you know how to handle the linear part. Clear? Good. Now, the similar question, ninth question, 6th and 9th are pretty similar question, but we have got x dx, same pattern. I'm going to write x minus 4, x minus 8 as x square minus 12x plus 32. So it will be 2x minus 12. So anyway, I'm going to write this as half 2x minus 12 plus 6. My answer. Right? Clear? Not clear? Everyone? Good. So till 9th, there is no issue. Now let's come to question number 10th. In question number 10th, what do you see? You see x into x square minus 1. Clear? And below you see x to the power 4 plus 2x square plus 5. So what should we think of? X square? If I put x square as t, good. So the first substitution which I am thinking of is to get rid of x to the power 4. I am not interested, but I see x to the power 4 with x square, so I can easily get rid of x to the power 4 thing by just substituting with x square. So if I put x square as t, my 2x dx becomes dt, which means my x dx becomes dt by 2. So now my new thing has become something like t square, t minus 1 into dt by 2, that is half out, upon under root t square plus 2t plus 5. We are very much aware of this thing, right? This is by quadratic thing, this is my linear thing. So I know what is the differentiation of t square plus 2t, that is 2t plus 2. So I can easily handle t minus 1 as 2t plus 2 and then, good. Good. So you know how to handle class 10th question. Now go to class 11th question. X cube into d of tan inverse x. You haven't seen d. You have abhi tak you were seeing dx, but now I put d tan inverse x. What does it mean, d tan inverse x? Okay, what will be the integration of this? If I put infinitesimal parts of tan inverse x together and integrate it, it will turn out to be tan inverse x. है ना? एक तो ये भी होगा, ये आइडिया होना चाहिए. दूसरा, if I say d of tan inverse x, I can easily convert this as dx upon. So I see x cube here, and I see 1 plus x square here, and I can see easily how to solve this question. Clear? Not clear? How to go for it? Put x square x dx upon 1 plus x square. Now you know how to solve it. Right? T upon 1 plus t form. T upon 1 plus t form, very easy form. Linear upon linear, the first questions which we were doing, right? Similarly, 12th part, the same question. I have already tackled how to solve x cube d tan inverse x, and I have already shown you how to solve d of tan inverse x. What is d of tan inverse x? Tan inverse x, simple. So I see 4x cube d tan inverse x, which I can easily handle, plus 2 times of d tan inverse x, that is 2 tan inverse x. Got it? Clear? Pakka, everyone is with me? Good. Now let's go for question number 13. Now when I told you that whenever you see x square plus 1, yeah, x square minus 1 in the numerator, and you can easily get the form of something like x square plus 1 by x square, what do you have to think of? X plus? You have to think of substitution. What do you have to think of u as? X plus 1 by x? Good. So I see that 13 as x square minus 1 dx. It's not that suddenly if you see x square minus 1, yeah, x square plus 1, you're going to jump into it. You're just going to observe that, okay, fine, is it going fine? So integration is some more like factoring. You have already told you initially, right? So you have to think how to go for it. So if you see x square minus 1, I'm thinking of, similarly जब हम लोग factorize करते हैं तो we think of disability test ऐसे, we take a hit and trial things, right? Similarly. So if I put x square minus 1 dx and we see x square plus 1 into under root x to the power 4 plus 1. So I'm thinking of x plus 1 by x. I'm able to grab du. So if I divide the numerator by x square, then only I get 1 minus 1 by x square. So I'm going to divide this also by x square. So, but I'm not dividing this by x square. I'm dividing this by x and this by x. So this will become x plus 1 by x, and this will become x square plus 1 by x square. Right? So I'm going to put x plus 1 by x as so something it will turn out to be dt by t into what is x square plus 1 by x square? T square minus 2. You know this form? What is this form? What is it? Derive it. Let's derive it. Okay. It will come out to be a very nice answer, and it's good if you keep it in your mind. I can say this as root 2 k square, right? I am seeing x square minus a square form, right? X square minus a square form. I'll remove root 2 out. So it will be like dt by t into under root t square by 2 t square by 2 minus 1 into 1 by root 2, है ना? Right? Now, t square by root 2, I'm seeing it as t into under root t by root 2 k square minus 1. Now, what should I select t by root 2 as? Substitute t by root 2 as sec theta. Why? That will become sec square minus 1. That will become basically tan theta. This will be sec theta. And you will get above sec theta tan theta. You will finally, everything will vanish. You will be left with dt. Let's do it. Should I rub the above part? See, so many concepts being used in this question only. So this is not that easy, which it looks like, as it looks like. So I'm going to put t by root 2 as sec theta. So my thing will become 1 by root 2. dt will become root 2 sec theta tan theta d theta. ये होगा ना? dt will become this one upon this is I'm putting my t as root 2 sec theta, and this will become tan theta. So this is gone, this is gone. I'm left with 1 by root 2 d theta, theta by root 2. What is theta? 1 by root 2 sec inverse t by. Okay, so up you can remember this formula: dx upon x into under root x square minus a. What will be it? Sec inverse x by a. Clear? You can easily derive it. है ना? It's very easy thing. You can keep in mind. So whenever you see something like dx upon x into under root x square minus a square, and also keep in mind whenever you see something like a square minus x square, substitute x as a sin theta or a cos theta. When you see something like x square plus a square, substitute x as a tan theta. And you see something like x square minus a square, substitute x as a sec theta. You know this thing? Okay, good. But you know how to derive everything. So where were we? So 12th we were in, 13th is done, right? Now let's go for 14th. When you see dx upon sine to the power 4x plus cos to the power 4x, what you are thinking? If I divide my thing by cos to the power 4x, this will become 1 sec to the power 4x dx into 1 plus tan to the power 4x. Is it anything which we are going close to? Are we getting close to anything? Any known thing? Are we getting close to something? What is that? If I divide it, this will become sec to the power 4 theta d theta upon tan to the power 4 theta plus 1. I can easily substitute now. My tan theta is u. So u square plus 1 into du upon, and whenever you see this form, you have to think of x plus 1 by x or x minus 1 by x. So I'm thinking of x minus 1 by x. So I can write this as 1 plus 1 by u square upon u square plus, so what should I substitute? U plus 1 by u should be, u minus 1 by u should be substituted by, let's say t. So I can say that dt upon t square minus 2. Yeah, no, just a sec. T square plus 2. है ना? Clear? Not clear? 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 Done? So, two substitution basically we had to do. है ना? So it's fine. You can do as many substitutions as you want, provided you are going to get closer to your answer, right? You're going to get closer to your known thing. Okay. Now, question number 15th. I see a quadratic thing upon quadratic thing. So I can easily break my above thing into the known thing, right? And then I get linear thing upon quadratic thing. And you know how to handle linear thing upon quadratic thing. Break that linear thing into the, should I solve it? Okay, wait. See, I'm seeing x square minus 2x. So I'm going to write this as half of 2x square plus x plus 2 upon 2x square plus x plus 2. Right? So I get something like x square plus x by 2 plus 1. But I have got x square minus x plus 1. So 1 has been handled out, but the x part has not been handled yet. So half x can be compensated by minus 3 by 2x. I can handle this part. I'm left with minus 3 by 2 into x by 2x square plus x plus 2 dx. I can again handle this by 1 by 4 into 4x plus 1. And then the constant thing. And then I'll get something like dx upon x square plus a square. Clear? Done? Open up, open up, open up. 3 or 4 steps, it will be opened up. Clear? Now let's go to question number 16. So it's very easy now, right? Question number 16. What should we do? Divide by. So we get sec square x dx. And in the denominator, we get 3 tan square x plus 4. So that becomes x square plus a square, right? Easy. Now 17th. Again, we see a linear form in the denominator. Linear form. So what should we think of? Half angle thing, tan theta. So we can say 5 into 2 tan x by 2 upon 1 plus tan square x by 2. So I can put my 1 plus tan square x by 2 in the numerator. That will become sec square x by 2 dx. We can handle that. And in the denominator, we find a quadratic thing. We can handle that. So we get something like dx upon quadratic. And we can handle that. Similarly, question number 18th, I have given you 3 cases. Right? Dx upon a plus b cos x. I've given you three cases. Evaluate for when A is equal to B, when A is greater than B, and B is greater than A. Okay. So should we solve it? Still 11:30 now. So we see dx upon a plus b cos x. Right? How to go for it? Okay, everybody can solve if 70 na? No issue with it. So let's solve dx upon a plus b into 1 minus tan squared x by 2 1 plus. So finally I get something like 1 plus tan square x by 2 dx upon a into 1 plus tan square x by 2 plus b into 1 minus, and this will become, so tan x by 2 is t, and sec square x by 2 dx becomes 2 dt. है ना? So now I can handle it. When a is equal to b, things will be very easy. Why? T square will be cancelled out. So a is equal to b can be easily done. Second case, a is greater than b. So it will be something like, let's generalize this first. 2 dt upon a plus b plus a minus bt square. This is the story. When a is equal to 0, this thing becomes 0. A is equal to b, this thing becomes 0. I can easily handle this question. When a is greater than b, this thing becomes positive. So it will become x square plus a square form. I can handle that. And if a is smaller than b, then it becomes a square minus x square form. I can handle that too. Right? Now if you see question number 19, you see linear upon linear, linear form of sine cos, linear combination of sine cos upon linear combination of sine cos. So how to go for it? Whenever you see I've given these two. If you see those, there is a difference, right? In 19th, you see no constant alone. And in 20th part, you see constants alone. So you must understand how to solve both the questions. So first, I'm going to solve 19th. When I say linear combination in both numerator and denominator of sin x cos x, I'm going to write my 2 sin x plus 3 cos x as L into sin x plus 4 cos x plus m into cos x minus 4 sin x. I can easily find my L and M, unique L and M. L and M nikal ke, I will get something like L into dx plus m into f dash x upon fx dx. So ln fx. So answer would be like lx. Answer would be L into x dx integration plus m ln sin x. Clear or not clear? Clear now? Good. This is how we are going to tackle when we don't see constants. And what will happen when there are constants? I can again go through the same pattern, but we will get something extra. Let's show you what. And when we get something extra, how to handle it. I can write my a sin x plus b cos x plus c as L into p sin x plus q cos x plus r. Quite easy to understand. Plus m into, what is the derivative? P cos x see, if you are going to balance, you will always find some constant thing. You will be able to handle sin x, you will be able to handle cos x, and you will be able to find unique L and M. But you will always be left with some constant, and that constant will be n. You know how to handle this, you know how to handle this, and you know how to handle n upon p sin x plus q cos x plus r. How to handle it? Tan x by 2 form. So you will be able to solve 20th question, right? Similarly, 21st and 22nd we have already discussed. It will be like more of a, okay. So you know x square plus 1 and x square minus 1. So how to go for it? X plus 1 by x and x minus 1 by x. So I can put this thing as 1 plus 1 by x square and this thing as x square plus 1 by x square. So I can put x minus 1 by x as my substitution. I see x square minus 1 upon x to the power 4 plus 1. So I can put 1 minus 1 by x square and x square plus 1 by x square. So I can put my x plus 1x as my substitution. Okay. Next sheet. So today we are done with the substitution part. The substitution was nothing but it was a reverse of chain rule. Now in the next class we are going to discuss by parts and then the rationalization and then the under root linear form, how to deal with it, right? So we'll be going to see more types in the next class probably, right? We don't have much time now, right? So any problem till here? Initially when we started integration, or maybe you have started in your school, when you were seeing that it was not like, it was something like you're mugging up or you're depending on the insights, but it's not more on the insights, right? Initially when we started, we were also light. And some of the, we also know the fact that there are functions which it is impossible to write there, irrespective whether it exists or not. Maybe it is non-integrable. Maybe the integration exists, like we have discussed the case of e to the power minus x square. Of course, there is a function whose derivative is e to the power minus x square. We have also seen the shape of that graph. It will be something like, so there are functions. So it is not only impossible, but it is not only hard, but it sometimes it is impossible to write that part. Okay, so you have already done the differential part. Now you should start browsing the differential questions also. Okay, and then we'll be subsequently after the getting exposed to the other types, we'll be getting into the definite integral. Okay, so integral calculus you have started. Good. Any question now? Should we call it a day? Okay, thank you.
No. Shall we start? So, welcome back to the part 2 of AC. And as I remember, yesterday I had given two problems for homework, 4 and 6, right? So, anyone tried 4 and 6? Online people, please post the answers. Question 4 and 6. The answers for them. आप लोगों का क्या आंसर आया? क्या नहीं आया क्या? You tried. Anyone else? क्या हुआ? ट्राई नहीं किया घर पे? ये लिखा ही नहीं था? नहीं लिखा था? वेरी नाइस. Root e square minus 1 upon so you are under root perfect बिल्कुल सही. For sixth नहीं किया. 6 नहीं हुआ नहीं या ट्राई नहीं किया. चलो लेट्स स्टार्ट. For fourth, it's the current given in an RC circuit. Do you remember what's an RC circuit? A series resistive capacitive circuit, right? So for that, like whenever it was connected, I'm just trying to make you guys recall this kind of circuit C, R, and E. However, initially the switch was not connected. It is connected at t equal to 0, and afterwards the current starts flowing. Okay. Initially the capacitor was uncharged, so the current is maximum, then it decreases. Right? Do you remember this? So for that we need to calculate the RMS. Even though the knowledge of this circuit is not necessary, it's just for your knowledge, for your information. Okay. Even if you don't know what's an RC circuit, it's still not needed. I have written the current function. So I is what? I naught E minus T by tau, where tau is time constant for the circuit. Okay, tau is time constant, and the interval given is 0 to tau. Okay, so let's first draw the graph, even though it's not needed, but drawing a graph gives you some sort of, at least it gives me some sort of mental clarity. So I generally try to draw a graph in most of the cases. So what would happen is starting current would be I naught, and it will drop off gradually. Not gradually, rather exponentially, I would say. Okay. So tau would be somewhere here, and we need to calculate RMS for this portion. RMS, not the average, right? So it's the current time. Okay. So let's start. Do you remember what was the procedure? क्या था? भूल गए एक ही दिन में? हाँ, मीन स्क्वायर पहले निकालते थे. ओके, एंड आफ्टरवर्ड्स आरएमएस अंडर रूट लेके. तो पहले मीन स्क्वायर निकालते हैं, विच इज व्हाट? एवरेज ऑफ आई स्क्वायर. एंड एवरेज मतलब क्या? 1 बाय tau minus 0 इंटीग्रल 0 to tau I square dt, which in this case would be I naught square E minus 2t by tau dt, like this. And let's bring this out. So integral 0 to tau E minus 2t by tau dt. And what would be the integral for this? Okay, यहाँ पे करते हैं I naught squared by 2 what e की power minus 2t upon tau upon minus 2 upon tau, t won't come, 0 to tau, right? Let's put the limits. I naught square by 2. When we put tau here, the value would be e minus 2 tau by tau, cancels. You would get e की power minus 2 minus what? E raised to power 0, which is 1. And the answer e raised to power minus 2. In fact, let's do one thing, 1 minus e raised to power minus 2 upon 2, and I multiply tau over. I take tau above, so this thing cancels. थोड़ा सा गड़बड़ हो गया. In fact, instead of tau, I accidentally placed a 2 here. Okay, right? So what we get, I naught square by 2, 1 minus 1 by e square. Okay, what would be RMS? I mean squared. So I naught by root 2 under root 1 minus 1 by e square, which is as good as the earlier answer I wrote, right? You can take the LCM, bring e out and take root 2 in. Is it okay? Anyone posted answers? So नहीं हो गया किसी से question, someone is asking a question. What is significance of time constant? Okay, see, for significance of time constant, we need to know the RC circuit. Okay, I just told you a little bit of glimpse of an RC circuit. You know, our resistance, our capacitance connected in series with a DC source across it. Okay, so this kind of circuit, I'm saying. Yeah, this kind of circuit with a switch which can be connected and disconnected, right? So what's the role of time constant? You know, time constant tells us how rapidly the current falls or how rapidly the capacitor, how rapidly the capacitor is charged, right? Mathematically, time constant is the time after which the current drops off to 37% of I naught. Mathematically, it can be calculated. You can put t as tau here. So after tau time, the value would be I naught by e. Okay, it's 37% approximately, or it's the time in which the capacitor charges to a value of 67%, 63%. Sorry, is it okay? 63%. The current drops by 63% and the charge rises by charge rises by 63%. I'll draw the graph. Let you guys just finish with this. Get over with this. I'll draw the graph for that. It's taught after capacitors. Just in current electricity, yeah, right after capacitors in current electricity. So, done with it? कोई और भेज रहा है कुछ? Erase करूं? Right. So for RC circuit थोड़ा सा बता देता हूँ. This is an RC circuit. Okay. So as the switch is connected, S and E is the E. As the switch S is connected, the charge rushes to the capacitor. But as you know that as the capacitor starts holding some charge, it prevents the entry of further charge. You know it, right? If there is some charge in the capacitor, it will prevent deposition of further charge. So as the charging process starts, initially the rate of charge flow will be more, but afterwards what would happen? It would drop. Why? Because if there is some charge in the capacitor, it would repel the coming charge. Okay, so the process would get slow and slow and slow, and finally it will be achieved after infinite time, which is what we can say that capacitor charges to 100% value only after infinite time, a long time. But for practical cases, we can take it as 3 tau, 4 tau. Like we can consider that after 3 tau or 4 tau time, the capacitor charges to almost full value. Okay. Graphically, if I draw, the charge versus time graph would be like this. This is the maximum value, Q naught. What would be Q naught? Q naught would be CE. Okay. Do you remember Q is equal to CV? Yeah. So final voltage of the capacitor would be V itself, E itself. Okay. So the charging process would be quick initially, then it would get slow and slow, and finally full charge would be attained after infinite time. So you can see that this graph is an asymptote. Do you remember what is an asymptote? Huh? Yeah, hyperbola. Do you remember this sort of graph, rectangular hyperbola? We say that it meets y-axis as well as x-axis after infinite distance, right? So this graph would be an asymptote. Okay, asymptotic curve, I would say. Asymptote is this line, horizontal line. And for current, current is what? dq by dt, right? Which is slope of this graph. As you can see, slope is decreasing and finally it becomes 0. So the current initially, which is I naught, would drop off and become 0 finally. After tau time, what happens is the charge attained after tau time, the charge on the capacitor becomes 0.63 Q naught, and the current, it drops off to 0.37 I naught. Okay. Okay. And the analysis, I cannot explain the analysis right now because it will take a lot of time, right? Okay, so by analysis, the time constant actually is RC. So you just need to remember the time constant. Its value is RC. So either of value, either whether it is more resistance or more capacitance, what happens is time constant becomes more large, which means that the circuit would take long time to charge to its 63% value. So you know, time constant is an indication of how quickly a circuit can charge the capacitor, right? Okay, okay, time constant is just an indication. So shall I erase it? And in this case, actually the x-axis becomes asymptote. You know this, right? Erasing it. So back to the questions. Question कर दीजिए. Question 6. Okay. The EMF applied across a circuit is given by E is what? E1 sin omega t plus E2 cos omega t. Find the RMS value of the EMF. Okay. अब देखो, can you see two sinusoidal functions? Right? Huh? So is it that difficult to calculate? Like, is it that difficult? We have yesterday we calculated RMS for one AC and DC combined, right? Let's try. But I need you guys to remember just one thing. You know, since we would be needing it again and again, let's calculate this. Do you remember 0 to t sine omega t dt? What's this? And what? Yeah. What if I do this? Do you remember this is the averaging function? कल ही किया था, हाँ? Averaging function से सिर्फ 1 by t I had removed. Okay, this is the averaging function. So I removed 1 by t thing. This itself. You remember that sine function? Yeah. Had positive and negative lobes. ऐसा कुछ. So area 0. You remember it, right? And for 0 to 2 cos omega t dt, what would happen? What? Let's plot it. This would be t by 4, t by 2, 3t by 4, and t. Okay. A positive part, a negative part, a negative part, a positive part. Area 0 again. You know, sine and cos are shifted graphs. They had been shifted through half time period, 1/4 time period. Sorry, they have been shifted. If I read this is actually what? Sine part shifted leftward. So this would be 0 again. Let's calculate 0 to t for sin omega t cos omega t dt. Do you know what this value would be? Can you calculate? And you will still toil and moil. यही होगा ना? Just now we studied के sine का graph, sine का integral over its period is 0. Here we have sine 2 omega t. It would have time period how much? Half or twice? Upon 2 total के नीचे है, it's a constant, it's not a part of the angle. This is a constant, half would be separated out. Half 0 to t sine 2 omega t. This has a period t by 2. Please remember this. Whenever a constant comes in numerator, okay, it decreases the time period by the same factor. Okay, and whenever a constant comes in denominator, it increases the time period by the same factor. So if we had 2 in the denominator like this, sin omega t by 2, कितना time period होता 2t, right? So we have what, this thing, this has time period half. So in 0 to 0 to t time, 2 cycles of sin 2 omega t would be repeated. In this much time, 2 cycles would be repeated. Okay, so in even when the area was 0 in one cycle, in 2 cycles it would be 0 again. So 0 again, right? Got it? Just the last thing, can I erase the upper part? What about this? The last thing, it won't be 0 for sure. Yesterday we calculated RMS, right? And you remember that it would be what? 0 t 1 minus cos 2 omega t by 2 dt, and half minus 1 minus cos 2 omega t dt, right? The value would be half t minus sin 2 omega t by 2 omega, 0 to t. Again 2 omega t, right? The area, remember the same thing? Do you guys? याद है ये चीज? 0 होगा ये, फिर से कल किया था हम लोगों ने, कितना आया? t by 2. And if you remember this, omega t was what, 2 pi by omega. So what we have here is pi by omega, right? You do remember this, okay? Let's use it here. Without these, this question had been a nightmare, would have been a nightmare, very long. Okay, but let's try, let's use this. We want to calculate RMS, which would be integral of, sorry, E we need to calculate. So E here would be E square sine E1 sine omega t plus E2 cos omega t whole square dt, right? Is it okay? Let's expand the square. E1 square sine square omega t plus E2 square cos square omega t. Okay, I am thinking of separating them as well, will make my job easier. 2 E1 E2 sine omega t cos omega t. Okay. Okay. What did I do? I opened the brackets, E1 square sine square omega t, E2 square sine cos square omega t, and 2 E1 E2 sine omega t cos omega t, right? Okay, then I separated the parts of integral. First integral would be this, second integral would be this, third this, and from this logic we can see what would happen to this. It would become 0. This would become 0. What about this? E1 square would come out. What would happen to this? 1 by t E1 square into what? T by 2 or pi by omega. Both the values would work. What about this? सेम होगा अलग होगा? सेम होगा? हाँ? See, अगर यहाँ cos होता, we would have what we would have done, प्लस यहाँ पे लेते, है ना? प्लस यहाँ पे रहता, प्लस यहाँ पे रहता, लेकिन ये टर्म तो जीरो हो गई. Okay, what matters to us is just the first term. वो अगेन सेम रहती, so इसका भी सेम आता ना. ये दूसरी तरह से भी सोच सकते हो आप. See, sine and cos graphs, they are shifted through an angle of pi by 2. Just that they have same areas under the curve. And what about their squares? Their squares would have the same thing, right? Okay. For one period they would have the same thing. नहीं, कल किया था मैंने ये चीज, ड्रॉ किया था. So this would be t cancels. What we get? E1 square plus E2 square by 2. And if you guys remember, yesterday I said कि आप लोग you can use the result directly. I said yesterday for fifth question, what I said that IRMS, what answer we got? Under root of I1 square plus I2 naught square by 2. This was the answer. Here the AC part had a contribution of this I naught, I2 naught square by 2. The DC part had a contribution this. We have two AC parts here. Both would have given the contribution this E1 square by 2 and E2 square by 2, right? So that's why the sequence, if someone had properly followed this question, you would have done that. Sixth one. Okay. Okay. So please, whatever you study here, please ghar jaake try it on your own. Even the solved questions. Okay. Not the unsolved ones. Not just the unsolved ones. Try the solved ones also, because they'll help you further. Okay. So shall we start? Okay, so before I start with part 2, I'll introduce something which is not related but related. Okay, we'll see the relation. Okay, right now you feel that it is totally unrelated, totally unknown thing. What I am telling here, what I am teaching here is SHM basics. Why? Why am I trying to push it in AC? Exactly. Do you remember the equation for an SHM? क्या होती थी? And our AC equation exactly the same, just I in place of Y and I naught in place of A. So slight bit of basics. Okay, SHM has projection of uniform circular motion. Okay, this was taught long back. नहीं याद नहीं होगा. So let us assume a particle P. Okay, a particle P is here. It starts moving in a circle centered at O. Okay, with constant angular speed. Omega is constant. Okay, its projection mark this diameter y dash. We would be taking projection on this one. So its projection here would be at the center. After t time, it would reach this point and cover an angle theta is equal to omega t. The projection would be here, and this would be same angle. So the distance of projection, yeah, I can say the displacement of projection from O would be how much? If we take A as the radius, then it would be how much? This length is A. By trigonometry, you can calculate it would be A sin omega t. Okay. Okay. The side in front of theta is always the perpendicular, right? Do you remember? Okay. This would be A sin omega t. And A is amplitude, omega is angular speed. You do remember this. Okay. What if the angle was not zero? ऊपर कर लो उसको, थोड़ा सा सामने आवाज आएगी, लो ठंड लग रही है। चलो, you guys focus here. See, what would happen if the starting angle was not zero? Initial phase. So if starting angle was not zero, let's say phi is the initial angle, and afterwards the particle covers omega t angle. So theta in this case would be omega t plus phi, and the displacement would be how much? Y is equal to, you guys do remember, okay? So from uniform circular to SHM, as the particle moves around the circle, the projection moves along this line up and down. It is an SHM, right? Okay. Okay. And you guys do remember that how the things map. The A radius here becomes amplitude for SHM. Omega angular speed becomes angular frequency for SHM. And phase, the angle theta here, the angle theta in circular motion, it becomes phase in SHM. Phi, the initial angle, it becomes initial phase or phase constant. Okay, the four quantities. What's the use in AC? That is now we are going to know phasors. So the next topic would be phasors. See, since the equations for AC as well as SHM are quite common, similar. So what we would do, we would start plotting AC wave in form of circular motion. Okay, so it would be like this. For EMF, E naught sin omega t, what we would say is, we take an arrow which corresponds to E naught length, E naught EMF, an arrow of length corresponding to E naught EMF. Okay, and since the angle here is omega t, we rotate it through an omega t so that the projection here is how much? Okay, same for the current, same thing for the current. So in this manner, what we have done is we have plotted EMF. This vector like thing, the arrow, it's not a vector actually. You know that EMF and current, they are scalars, right? So this vector like thing, this is called a phasor. Okay. So what we have done is we have plotted EMF as well as current in form of rotating phasors, like we did in case of SHM. So this thing would be rotate. This thing used to rotate. The radius here used to rotate like this. Okay. Here the phasor would rotate like this. Okay, and the projection would give you the value of AC. So this would be the phasor for EMF, and the phasor for current would be similar but a little smaller in size. Generally we assume that EMF is larger than current in magnitude, numeric value. Okay, so this much, you are okay with it? Shall I erase? Okay. Which one is more dangerous, 220 volt DC or 220 volt AC, and why? Okay. See, you said which one is more dangerous. Okay. So, वैसे तो it is said that 220 volt AC is more dangerous, but let me clear the point for you. You know, dangerousness of a voltage, it's not clearly measured. It's the current actually which is dangerous. Okay. So whichever of them drives more current is dangerous. You know, household AC, it drives a current of 1 ampere, 2 amperes. Okay, right? And when we rub cloths on carpet, like when we rub our feet on carpet, you know, our body gets charged to a few hundred volts. Okay, it can produce a single spark which can start a car battery, if done properly. Okay, a single spark. But that spark, did it kill you ever? I mean, like this you would have witnessed at your home, sitting on a chair, somebody comes in and touches you, and there's a spark, tiny spark. Did it ever kill you? No, but AC may. Why? Because in this case, in the case of a spark, the current driven is very small. So it's the current which matters. So if you say that 10 volt DC or 10 volt AC, then the question would have been different. 10 ampere, sorry, 10 ampere DC or AC. Okay, that then I would have compared, you know, 10 volt, 10 ampere AC means RMS value is 10. So that means that at that time both would have been equally dangerous. Okay. 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 Shall we come back to the point? So phasor. अच्छा अब another thing I would like to pick from maths. Okay, do you remember complex numbers? Do you remember the you know, the representation, phasor representation in Argand plane? Do you remember? ऐसा कुछ होता था, Z with an angle phi or theta. Okay, Z was the magnitude and phi was argument. Okay, so we used to represent it as Z angle phi. ऐसे ही होता था ना, where this Z is magnitude and phi is argument. Okay, in our case, since omega t, the angle would always change, so there is no point taking omega t as the argument, right? Because it would keep changing all the time. Okay, what we would take is what we would take as initial argument is initial phase. Okay, so let's say initially at t equal to 0, the voltage was like this. Okay, initial phase 0, E naught. Okay, so if we plot E bar, it would be like this. This is the magnitude, and 0 degree is what? The initial phase for a current of this type. Let's say current has an angle 60 degree initially at t equal to 0. The phasor for I would be what? I naught angle 60 degree. Okay, 60 degree is the phase. Okay, why I'm doing this is because this makes dealing things easier, the complex representation. Why? Because we would be dealing in resistances and those reactances, sorry. Okay, we would be dealing in resistances as well as reactances. You know what is reactance, but you do know that reactance comes in picture when the current when the AC current flows, right? Okay, and it's not exactly like a resistance. It blocks the flow of current, but it never consumes in power, right? We'll see. Okay, so it's kind of imaginary resistance. So that's why this complex kind of representation we would be able to do that easily then. Okay, continue. So when AC EMF is applied across pure resistance, okay, okay, AC EMF applied across resistance, a current I flows. The value of I is what? E by R. Okay, in terms of phasors, yeah, just we'll draw the phasors later on. It would be what? Directly we can say this, which is what? I naught sine omega t. Okay, I naught is the peak current. Okay, and as you can see, the EMF has no initial phase, the current also has no initial phase. So yeah, exactly, if I draw EMF E naught, phasor of EMF like this with an angle omega t, I would have to draw the current phasor I naught overlapping at t equal to 0. E naught I naught, right? Okay, so in phase manner, what would we be doing? I would be what? I naught 0 degree, and E would be what? E naught 0 degree, right? And what about resistance? If we represent resistance as a phasor, it would be what? E naught by E phasor by I phasor. Okay, and what? R angle 0. Okay, how? You remember that when complex numbers used to divide each other, the magnitude was divided, but the arguments were subtracted. You do remember, okay? And multiplication the magnitudes are divided, multiplied, and the arguments added, right? Okay, we would be using that. Here actually both the angles were 0, so taking a difference, actually subtracting them from each other, would have made no difference. That's why 0 degree. For further cases it would actually. So is it okay? You guys are writing, so okay, done. Right, okay. You know, charge, since EMF is E, charge at any time would be Q is equal to CE. You remember Q is equal to CEV form. Okay, so it would be C E naught sine omega t. Okay, what the current? What about the current? dq over dt? C E naught omega cos omega t. If we take this as I naught, the thing becomes like this. Okay, and this can be written as what? Omega t plus pi by 2 or minus pi by 2. If we take minus, it would go in fourth quadrant, in which sign is negative. Okay, so plus pi by 2, we can see here that an initial phase of pi by 2 is introduced. So this phasor for E would be what? E naught angle 0 degree. Okay, and the phasor for I would be what? I naught angle how much? Plus pi by 2. Okay, so the phasor diagrams would be at t equal to 0. At t equal to 0, if this is the EMF phasor, the current phasor would be here, angle 90 degree, both rotating through same, both rotating with same angular speed. Okay, I naught, right? After t time, the phasor would be, this is E naught phasor with an angle omega t. So the current phasor would be like this, I naught, 90 degree angle maintained. Okay, both rotated through the same angle. Now this you already know. Okay, so let's see what is, in this case, what is E by I. Okay, this is a purely capacitive circuit, right? And we don't we know that a capacitor, pure capacitor, has no resistance. Okay, what is E by I in this case? Let's see. E was E naught sin omega t. ठीक है, या इसको ऐसे लिखते हैं, एंगल 0 डिग्री, and I is what? C E naught omega angle plus pi by 2. Okay, so this thing would be what? 1 by omega c angle minus pi by 2. 0 minus pi by 2 is minus pi by 2, right? Okay. So this thing, since you know E by I has units of ohms, okay, has units of ohms. So this thing would have units of ohms. Let's call it xc, 1 by omega c. Okay. This thing is called what? Capacitive reactance. Okay. Since it has units of ohm, we call it capacitive reactance. Okay. It is the ohmic opposition to current. What? Ohmic opposition to the current in AC circuit due to a capacitor. Okay. And we have calculated the phase also. So the representation would be for xc, the representation would be, if we draw the reference line here, xc would be downward. Okay. For resistance, you do remember that it would be horizontal because the angle was 0. Okay. Done with it? Done. Shall I move? Pure inductor. Okay. Can I raise everything? It is still the same. Okay. In this case, you know that the current here would be changing. Since the EMF applied is a changing, a time varying EMF. So the current would also be time varying, and due to that, an induced EMF would be generated in the inductor. You know it, right? And since these two are connected in parallel, so what we can say is both would have same voltage across them, which means L di by dt is equal to E, okay, or E naught sine omega t. Why? Because VL is equal to E parallel. Okay, and you know di would be how much? E naught by L sine omega t dt. To calculate current, we would need to integrate it. Okay, let's do an indefinite integration. I would be E naught by L minus cos by omega plus C. You do remember, okay? This constant C, you know, everything else is a time varying function. This thing is E naught by omega L minus cos omega t plus C. Okay, this part is time varying. This C is constant. So whatever the time may be, C would remain same. Okay, is it okay? It is a constant. So do you remember that the AC sinusoidal AC current has an average value 0? If C is non-zero whole of the time, how would the average be 0 then? Getting my point? Getting my point? Okay, this thing is a variable thing and this thing is constant. We yesterday calculated that average value over a period or over multiple periods for an AC current is 0. Voltage also, they are 0. The thing remains same even if there is a phase involved. Okay, I told you yesterday that even if there is some phase involved, the average would be 0. So if C is non-zero, for average it would add up whole of the time. What do we do in average? We take we add all the values and divide it by n. So it would add n number of times and get divided by n. It would remain In the end, the average won't be 0 if E is non-zero. Getting my point? So since I, the average of I should be 0, and you know this cos omega thing, it would also give an average 0. So C should also be 0, so that the average becomes 0. Here I'll write I average is 0 for sinusoidal AC, even if phi not equal to 0. Okay. If C not equal to 0, the would not equal to 0. Okay. If C is not equal to 0, average of I would not be equal to 0. Okay. I told you just now. So C would be what? 0. Okay. The other thing, this has average 0, but C, it won't have average 0 until unless it itself is 0, because it won't change, its value won't decrease or increase, its value would remain same. Okay. So let's remove C from the situation and let's try to change it a little bit. E naught by omega L minus cos omega t tha, like this. Okay, we can write it as sine omega t minus pi by 2. Okay, it's in the fourth quadrant, the value would be negative, so we have taken care of negative sign as well as cos. Okay, if we take this as I naught, what we are looking at, the phasor thing would be I naught angle minus pi by 2. Okay, or I naught sine omega t minus pi by 2. Right? Shall I erase this? इधर का पार्ट लिख लो फिर. ये जो क्रॉस होते हैं ये क्या है, मतलब जो ऑफलाइन they have not started the video. Okay. Okay, they are not online right now. They are listening to you. But they have not started their video. Okay. Okay. So okay. So they can see the video, but I won't be able to see them. Right. Okay, done. Shall we start? Okay. I'm erasing this part. Okay. So the phasor at t equal to 0, it would be what? We have E, which has initial phase 0, and current which has initial phase minus pi by 2. So E naught here and I naught here. After t time, the situation would be like this. This would be E naught omega t. This would be I naught. 90-degree angle maintained, both rotating with same angular speed. Right? This you already know. Let's calculate the E by I thing. Okay, this is what? E naught angle 0 degree by I naught angle. In fact, let's not take I naught. The value is E naught by omega L angle minus pi by 2. Okay. This is the maximum value of current I naught, the peak value, and rest part. Out of rest part, we have the importance of only minus pi by 2, right? The initial phase. So this thing would be omega L plus pi by 2. And you know, since E and I, like voltage and current, when the ratio is taken, the units are in ohms. So this thing would have units in ohms. We call it XL. You already know it, right? Inductive reactance, okay, XL. We know the phase. So XL, the phasor for XL would be like this, positive. Okay, the phasor for XL would be like this, positive. Okay. XL is, you do remember, right? It is the ohmic opposition offered by an inductance. Okay, when connected in an AC. Shall I raise? What if RC are connected in series across an AC source? A common current I would flow. Okay. Okay. A common current I would flow. Okay. This thing has no, this thing introduces no phase change, but this would try to introduce a phase change of how much? Pi by 2 or minus pi by 2? Plus pi by 2. It leads the current. It makes the current lead actually, right? So we can represent it in this way: the resistance and the reactance Xc, a box, okay, kind of a resistance, but not exactly. The graph would be how much? This is R, the phasor, okay. The phasor would be, for R angle is 0, for Xc angle is how much? Plus pi by 2. Okay, so like this. Okay, the phasors, they do get added. The phasors, they do get added, and what do we get? Z as a phasor would be what? R angle 0 degree plus Xc angle plus pi by 2. The resultant angle would be how much? It would be, the value would be under root R square plus Xc square with an angle how much? Tan phi is what? This is Xc upon R. So the angle would be plus tan inverse Xc upon R. Okay. So you can see actually phi would be less than pi by 2 but more than 0. You can see the capacitor will try to make the current lead, but the resistance would try to maintain the phase, okay, keep them in same phase. So what the result would be? Some mediocrity would reach, okay, middle ground would reach. They would have some angle which would be in between 0 and pi by 2. So if we draw the phasor would be, this is E naught and this is I naught, the angle phi, and both rotating Okay, so after omega t, what would happen? You can just know now. Okay, both would rotate through the same angle. Okay, done. The current in this case would be what? E bar upon Z bar. The current would be how much? अच्छा, टेल मी वन थिंग, तुम लोगों ने मुझसे गलती कराई ना, ये प्लस था क्या? हाँ, एक्सी क्या होता था? For XC, current used to lead. This was E naught and this was I naught. And that's why XC was drawn downward and the angle was minus pi by 2. And I followed your words and you had been writing also. But then, चलो अब देखो, ये नीचे की तरफ बनेगा डायग्राम. क्या? करंट को लीड कराता है ना, लेकिन एक्सी फिर उल्टा होगा. डिवीजन वाला फैक्टर सोचो ना. एक्चुअली ये सोचो, E has 0 angle and current has plus pi by 2 angle. Okay, so E angle 0 by I angle plus pi by 2. ऊपर जाके it would become minus pi by 2. So XC has an angle of minus pi by 2. Okay, so बहुत गड़बड़ करवाते हो तुम लोग. Values would be same, but the sign would be minus, negative. Okay, this would be plus tan inverse XC by R. Okay, okay, just one diagram में correction. ठीक है, ठीक है, ठीक है. करें आगे हैं, आरएल के लिए करें, फिर कुछ क्वेश्चंस करेंगे. चला इरेज. Okay, series RL circuit. E is E naught sin omega t. Okay, R would be actually like this, and XL would be actually like what? Plus pi by 2. Okay, let's recall. ऐसे होता था E naught, current lag करता था. That means XL would be on the upper side. Okay, opposite होता है करंट के हमेशा. ठीक है, अब ये होगा, so impedance would be what? R angle 0 plus. चलो ये डायरेक्टली लिख लेते हैं. Let's draw the graph, the phasor. This would be R, XL ऊपर की तरफ. Tan phi would be what? XL by R. Okay, do you remember this thing is called impedance triangle? Okay, this thing is called impedance triangle. Here is Z. So Z would be how much? under root r square plus xl square with an angle plus tan inverse xl by r. Okay, and the current would be E bar by Z bar angle how much minus tan inverse xl by r. So the phasor for current would be here, it is E naught, current would lag, see the angle. Okay, this is phi, right? Just finish it. Shall we continue? Okay, let's try our hand on some questions. Okay, एक और जो स्कैन दिया था मैंने अगला वाला या एग्जैक्टली यही वाला, थोड़ा सा इसको नॉर्थ कर दीजिए बस. थोड़ा सा जूम आउट कीजिए, एक्चुअली कट जाएगा कुछ हिस्सा ना, साइड में लिखा हुआ है. एक स्टेप बस. ठीक है, अब हो जाएगा. ठीक है, डिस्प्ले तो वहाँ पे ठीक हो रहा होगा, ये थोड़ा फेडेड है कल की कंपैरिजन में. ओके ओके, shall we continue? First question. When 100 volt DC is applied across a solenoid, a steady current of 1 ampere flows in it. Okay, when 100 volt AC is applied, current drops to 0.5 ampere. Okay, the frequency of AC sources given 150 root 3 by pi hertz. Find the resistance and inductance of solenoid. ठीक है, it's an easy question. All right, people, the answers, and you here, किसी कुछ R100 होगा तो आसान है. how much it is? Correct, correct. I नहीं है actually, L है. 1/3. Okay, so it is given, you know, a pure solenoid has no resistance. So if a DC is applied to pure solenoid, okay, in steady state, it would allow infinite current, right? In this case, in steady state, a current of 1 ampere is flowing, which means that there must be some internal resistance of the solenoid. So it is actually a solenoid with some internal resistance R. When DC is applied in steady state, you know that actually the inductance, it plays no role. Okay, only the resistance comes in picture. So the current in DC state would be what, 100 EDC by R, or 100 by R, given as 1 ampere. R is what, 100 ohms, easy. Okay, in case of AC, in case of AC, both inductance and resistance, they play their role. Okay, so you know, inductance would create inductive reactance and resistance would oppose itself, has its own opposition. So Z in this case would be how much? XL R square plus XL square. Okay, we don't know it right now, but as in case of AC, the EAC by Z, this is given as 100 by Z is 0.5. Okay, we know that Z would be what, 100 by 0.5 is what, 200 ohms. Okay, so using this, under root 100 square plus XL square is 200, or 100 this, like this. Okay, which means XL would be 30,000, XL square would be 30,000, making XL as 100 root 3. And you know XL is omega L, and omega is what, 2 pi f. So omega L is equal to 2 pi f L is 100 root 3. 2 pi, frequency how much is given? 150 root 3 by pi is equal to 100 root 3. Okay, L was there also. Okay, root 3 cancels and this thing would give 3. L would be 1 by 3 Henry. Okay, try the second. Angle 5 by 12. It's correct. Done? नहीं. Circuit impedance is 13 and the angle is 5 by 12. Tan inverse 5 by 12. LR सर्किट ठीक है. इससे स्टार्ट करें. स्टार्ट करें. शैल वी स्टार्ट. चलो सीरीज एलआर सर्किट बोला गया. एल और आर दोनों की वैल्यूज दी गई हैं. ठीक है. ईएमएफ एंड फ्रीक्वेंसी सब कुछ गिवन है. एल इज 175 by 11 millihenry, which means XL would be 2 pi f L. Frequency given is 50. E is 130 root 2 volts. Frequency given is 50 hertz. Okay. Actually, pi is 22 by 7, right? हाँ हाँ, पाई नहीं होगा. 11 एक्चुअली यहाँ से कैंसिल हो रहा होगा. जस्ट सी 2 pi f L. पाई होगा 22 by 7, f होगा 50 एंड L कितना होगा 175 by 11 मिली हेनरी था. सो 10⁻³ सो कितना होगा ये 25 2. ओके. कितना हुआ. इसको ऐसे लिख लेते हैं 1/1000 यहां से एंड 4 कैंसिल सर 5 बचा एंड में ये वाला. सो 5 ohms. XL is 5 ohms. Z would be under root R square plus L XL square. How much? 13. Easy. And do you remember tan phi होता था how much? XL upon R. R and XL किस तरफ होता था. अब दोबारा बताओ. XL किस तरफ होता था. नीचे होता था. ओके. पक्का. फिर गलत. याद करो फिर से. E नॉट ऐसे होगा. करंट लैग करेगा इसमें. ओके. इंडक्टर लैग्स करंट. ये होगा. इसके उल्टा होना चाहिए था ना. रिवर्स ऐसा होना चाहिए था. एक्सेल. अब एक बार गड़बड़ कर दिया मैंने. बार बार थोड़ा गलती करूंगा. तुम लोगों से पूछिए. एक बार गलती की दोबारा थोड़ी करूंगा. दिस टाइम 5 वुड बी कितना होगा एक्सेल यानी 5/12. ओके. यही चाहिए था. करंट ये है E नॉट. तो करंट नीचे की तरफ होगा 5 एंगल से. ओके. ईएमएफ एंड करंट. थर्ड करें. ऊपर कर दीजिए थोड़ा सा. करंट इन सर्किट भी अगर निकालना हो तो यू कैन कैलकुलेट. E इज गिवन, Z इज गिवन 10√2 है ना. This one is easy as well. देखिए जरा चैट में कुछ आ रहा है कर लियो चलो effective current गड़बड़ सब गड़बड़ someone has posted a question, can we get current by dividing by R? No. The answer is no. We can divide by R only when the circuit is purely resistive. Okay. We can get for this question, we can get current by dividing EMF by resistance only in purely resistive circuits. When we have impedance, we need to divide EMF by Z. Okay. 10 ampere is the correct answer. And 10 ampere, would it be the peak value or the effective value? What is the effective value? कल बताया था RMS. So would this be the RMS value or the peak value? Peak. अच्छा, just tell me one thing. घरों में जो supply आता है ना 220 volts AC and 50 hertz. That 220 volts, is it the RMS value or the peak value? RMS. So यहाँ कैसे peak value बता रहे तुम लोग? It is given that the AC source has EMF 500 volts. Okay, so that 500 volts is what? The RMS value. Okay, peak value is specially mentioned. Okay, if the question wanted to give the peak value, it would have said the AC source has peak value 500 volts, right? So what is given here is the RMS value. Somebody has posted a wrong answer. 10 by root 2 is not the correct answer. It is 10 only. 10 what you have got here is the effective value or the RMS value, right? Okay. The peak value would be 10 root 2. R is 40 ohms. Shall I solve? हाँ हो गया होगा सबका है ना? For those जिनका नहीं हुआ, R is 40, C is पहले कुछ और values लिख लेते हैं. E is 500 volts, F is 120 hertz, and C is 1250 by 9 pi. Okay, microfarad, which means XC would be 1 by omega C or 1 by 2 pi FC. 1 by 2 pi 120 into 1250 by 9 pi into C is in microfarads, so 10 to the power minus 6. Okay, pi cancels with pi. It would be 10 to the power 6 by 4, 3, and this. नहीं ये नहीं कटेगा, हाँ ये ऊपर चला जाएगा. Okay, so 3 would go up, 3 into 10 to the power 6, and this would be how much? 8 into 125 with 2 zeros remaining as well. Okay, 4, how much? This whole thing would be 1000. Okay, so this would cancel 3 more zeros, it would be 30 ohms. Okay, so the capacitive reactance is 30. Z is under root R square plus XC square. 80 कहाँ पे आना चाहिए था? 1250 into 8 twice is 250. Okay, and 4 times is 500, then what? It would be 1000. So 40 square plus 30 square, 50 ohms. So current would be, acha, current, did you express current in the phasor form? अच्छा, phase difference अलग से ही हुआ है, ठीक है. I would be what? E by Z or 10 ampere. Tan phi would be how much? XC by R. And let me check the diagram first. Again, क्या होगा diagram? Would it be positive or negative? चलो, let's go with the procedure. Standard procedure. E naught. Current नीचे होगा ऊपर होगा? Current would be this XC would be चे ये R इधर. So angle would be like this on the negative side, right? So 30 by 40 is 3 by 4, which is, so phi is 37 degree. Do you know about this triplet? 3, 4, 5 triplet, Pythagorean triplet. In this triplet, the angle is 37 degree and 53 degree. No, actually ये 3 होना चाहिए था. Okay, in this triplet the angles are 37 and 53. So 3 by 4 would be at an angle of 37 degree. The phase is 37 degree. If we want current in phasor form, I in phasor form would be how much? 10. Just tell me how much? 10 angle what? How much? Plus or minus? This angle is minus. So minus 37 degree. Is it correct? Have you been following whatever I was saying? This is 10 root 2. Okay. Okay. In phasor form, how do we express the peak value? Because the peak value phasor that rotates. Okay. So the peak value along with the angle. This would be the phasor form, right? So let's try the fourth one. पूरा नीचे कर लो, सारा नहीं हुआ है अभी. हाँ, नहीं आ रहा. ये कैसे होगा यार फिर? अच्छा, स्कैन में कट गया क्या? चलो, I'll write the last line. Okay. Shall I erase this one? Shall I erase this one? They have answered the first part actually. The second part is the interesting thing. नहीं होगा, नहीं होगा. I think ये स्कैन में ही कट गया शायद. Yeah, now it is. So now part A and part B both you need to do. It has two parts. First one is circuit impedance. Okay. In first part, you need to find the circuit impedance. In the second part, however, you need to find this potential difference across points A, B, where A and B are these 2 points, and it is at a time when the value of VAB is half of the source EMF. You need to find the time as well. So the second part is really interesting. That's what I'm looking forward to. सेकेंड पार्ट भी है ना. फर्स्ट पार्ट का बता दो. इट्स ओके. Exactly. Correct. Did you express them in phasor form? Phasor form would be a little difficult. Getting the values is easier, but it portrays a wrong picture actually. I'll tell you what exactly would happen. Phasor form is that E naught angle something wala form. So try to do it in that form. I want answers in that form. अच्छा ब्लिंक करने लगता है क्या? ए व्यू में ब्लिंक होने लगेगा. ओके. देखिए प्रॉब्लम विद 4√2 and 4√2 answer is that it makes you think that these values are attained at the same time, which is not correct. They won't achieve their peak value at the same time. They won't achieve their RMS values at the same time. That won't happen. So that's why I want the answers in phasor form, so that you may know how much lag is there, what is going on actually. Okay. Otherwise, if you calculate, if you add them up, 4√2 for this one, √2 for this one, and 4√2 for this one. So how much would the total be? Tell me. 9√2. Okay. It is more than the source EMF. समझ आया क्या कह रहा हूं? My point समझ आया कि अगर सेम टाइम पे 4√2 and 4√2 अटेन हुए होते, okay, that means the total EMF, total voltage across all the three components would have been 9√2, which is more than the source EMF. How is it that? How is it possible? How is that possible? हाँ वेक्टोरियली ऐड करते हैं, which means वेक्टोरियली means अलग अलग टाइम पे ये चीजें हो रही होंगी, है ना? Okay. So that's why I asked the thing in phasor form. जानबूझ के आया किसी का आंसर in phasor form? नहीं? You guys followed everything in phasor form, right? हाँ? चलो अच्छा. I'll solve the first part, okay, but you guys would have to try for the second part. Okay. Fourth, first part हम कर रहे हैं. This is E, 8 ohms, XC is 2 ohms, and XL is 8 ohms again. So I saved the workout, right, for you. I already have given the values. So let's draw the impedance triangle then. If three possible, if three circuits are there, then what would happen for XC? How much was the phase? R is in this form. कौन ऊपर होगा? फिर गलत फिर गलत. For C, current is above, so XC नीचे होता है. And for तुम इससे याद रखो, ज्यादा अच्छा रहेगा. Okay, so XL would be क्या होगा? नीचे की तरफ XC, ऊपर की तरफ XL. इफेक्टिव X कितना हुआ? X कितना हुआ? 6. So ये कितना आ जाएगा? 10. Z is how much? Under root R square plus X square, which is 8 square plus 6 square, यानी 10 ohms. Okay. Angle X by R. X is 6 by 8, sorry, 3 by 4. So angle is 37 degree. Okay. Okay. So Z, if written phasor wise, it is what? 10 angle how much? Plus 37 degree. Okay. We know current. I phasor would be what? E phasor by Z phasor. E phasor how much? Was how much? कितना था? 10. 10 or 10 root 2? 10 by root 2. इसको ऐसे लिखते हैं, याद हो. पीक वैल्यू लेते हैं हमेशा, राइट. 10, दिस इज Z एंगल प्लस 37 डिग्री. कितना होगा? 10 by 10 एंगल 0 डिग्री बाय एंगल 37 डिग्री. ओके. करंट होगा 1, आप लोगों ने निकाला, राइट, बट यू डिडंट कैलकुलेट द फेज एंड दैट्स व्हाई फंस गए. फिर फेजर फॉर्म यू वर नॉट एबल टू कैलकुलेट. अब नाउ लेट्स सी के इन फेजर फॉर्म व्हाट वुड बी voltage across R, L and C. Okay, I am erasing the diagram. We don't need the diagram, it's over there. I don't have space actually on the board. So we are in phasor form would be I in phasor form with R in phasor form. Okay, how much? 1 angle minus 37 degree with 8 angle 0 degree. Okay, and you know in phasor forms the angles are added, the magnitudes are multiplied. Already you know 8 angle minus 37 degree. Okay, so VC was the second thing. VC phasor is I into XC in phasor form. Again 1 minus 37 degree with XC. XC is always in minus pi by 2 form. Okay, in the downward direction, negative phase. So XC is 2 angle minus 90 degree. How much? 2 angle minus 127 degree. So if you want to express it in sine wave form, the value would be 2 sine 100. Acha, okay, we started with cos, so we would have to continue with cos itself. 100 pi t minus 127 degree. Is it okay? Okay, and for VL what would happen? क्या होगा? बिल्कुल सही, XL. So 1 angle minus 37 degree and 8 angle plus 90 degree, right? Okay, so कितना बचेगा 53 degree, right? Okay, it would be 8 angle plus 53 degree volts. This would be volts or 8 cos 100 pi t plus 53 degrees. Okay, so the answer is in phasor form. Now try out the second part. Potential difference across the points AB when its value is half of the source EMF. कितना होगा? हाफ है. So listen, देखो पहली चीज तो देखो ये एंगल्स का हेर फेर समझ आया आपको? ओके, अगर मैं इसको डायग्राम पे ड्रॉ करूं फेजर पे, it would look like this is VR, this is VC and this is VL. Okay, ऐसा हो रहा है. The resultant यहाँ पे ये V बचेगा and the resultant would be like this. Okay, you know it. So these values, the rotating phasors, they will meet the x-axis at different times, है ना? Okay, and they'll meet the y-axis at different times. You know, when they meet the y-axis, their projection on y-axis is maximum, right? So even though these values are, we have these values, these values are available, but right now at this point of time, the total value will not be this plus this plus this. Okay, because it would be what? The projections only. We need only the projections here. So out of three quantities, the one which meets the y-axis, it casts the biggest projection, so it has the largest possible voltage. So with time this thing changes, right? Whole of the arrangement this rotates and different values cast big projections at different times. Okay, so the thing would be achieved at some time, this thing, but you cannot directly say that the value would be 5. Okay, I can say, what I can say at max, that at any time t, the voltage VAB, at any time t, the voltage VAB would be how much? 5 cos 100 pi t. I cannot forget the cos thing. Okay, the voltage would be 5 cos 100 pi t. Okay, and VAB we also know through this, we have two components in between. Okay or not okay? ठीक है? Okay, so we know VAB through this method also, I into X phasor. Okay, so these two values you have to equate, these two values. So you would get the time when the thing happens and you'll get the value then. Continue please. Someone is कुछ flash हो रहा है. Yeah, sure. Yeah, please. Yeah, please. Yes. आवाज नहीं आ रही आपको? Yeah, I can hear. I can hear you. क्या हो रहा है? I can hear you. Can you hear me?
Hello?
Yes.
Hello? Sir, I had a question that resistance is not a vector. So
It
while calculating impedance, why do we use it, treat it as a vector?
actually they are not vectors. None of them are vectors. We are not dealing in vectors, right? Voltages as well as currents, both voltages and currents, both are scalar quantities. Okay, but since the angle is changing, omega t is changing, there might be initial phase. We treat them like phasors, rather complex numbers. They are not treated like vectors. We treat them like complex numbers in Argand plane. Okay, that makes our analysis easy because as I told you like 30 minutes back that in SHM the equation is of this form. Okay, it's a projection, it's the displacement of projection of a particle in uniform circular motion, right? So for an AC, same kind of thing exists, right? Okay, we saw that even this can be, even the projection thing can be used for this. The projection thing can be used even for AC. We saw that projection of the maximum current, the peak current on y axis, it always gives the current value, which is this value. Okay, so that's why we are dealing this. We see this correlation, and that's why we use it to make our things easier. Okay, you already know the rotating phasor form. Okay, you have studied it in your NCERT books, but we are taking it a step further. Okay, we are taking it a step further. We are using it in calculations directly, the angles. Okay, they are not vectors, but to show you that most of the times what we think that scalar quantities they act directly, but here we can see that the scalar quantities they cannot be added directly because they have different values at different times. So to include the sense of angle, we use this phasor format. Okay, it's not a vector, right? Please explain the phasor part. Okay, okay. See, erase this as well. Okay, as I said that SHM projection, थोड़ा बड़ा लिख देता हूँ. As I said, uniform circular motions projection can be used for SHM. Okay, the values map, the radius becomes amplitude here and so on. Okay, the initial phase, the initial angle here becomes initial phase. Okay, so if we represent, if we have a look at the equation of SHM, it is of this form. Okay. The equation of SHM is of this form. The equation of AC current is of the same form. Okay, we see a correlation sin omega t. Okay, even though in AC there is nothing rotating. Okay, nothing is in circular motion, but what we do, we can use the same kind of representation for AC. What we can do is we can take I naught as a line segment, arrow line segment. It's not a vector. Okay, it's just a line segment with an arrowhead. Okay, with its tail fixed and it is rotating with a uniform speed omega. So the angle here is omega t, and if we take the projection, it is I naught sin omega t. right? So this projection thing, this get to know, okay, okay. So if there is some initial angle, if there is some initial angle, let's say this much was the initial angle phi naught, and the rest is the angle covered, the angle would be sin omega t plus phi naught, okay. Is it okay? Okay. And if you see this kind of representation, you have seen this already in case of a complex number, okay. This was the argument, this was the mod, and this was the argument. The difference in our case is that our phasor would be rotating all of the time, and in complex number, you know, the arrow was static, okay. So what we do is we use this form for our purpose, but at time 0, okay. At time 0, the omega t thing would be 0, only the initial phase would be there. So we represent this initial phase in complex form, and if you remember, the complex form was this, the complex number form was this. So we use the same thing in AC, okay. So agar if we say that initially the current phasor has an angle phi initially, okay, at t equal to 0, we can represent it in the complex notation as I is equal to I naught angle phi, okay. That's what we have done, and we can use the same algebra as the complex numbers, okay. For multiplication, you remember that what we used to do, z1 z2 used to get multiplied, the mods used to get multiplied, and the arguments added. For division, the mods they used to get divided and the arguments subtracted. So that form we use directly. For this question, we earlier calculated z along with, for this question we earlier calculated z, which was 10, along with the phase, the initial phase, which was how much? Tan inverse x by r, positive or negative? फिर भूल गए, okay, plus tan inverse, okay. Now since we know z, I would be E bar by Z bar. E had no initial phase, so representation of E is like this, and representation of Z is like this, tan inverse x by r. So this thing becomes negative, okay. The angle, the argument becomes negative by going up. So E naught was given as 10, so the thing becomes minus 10 tan inverse x by r, and x was 6, r was 8, so we know the angle is 37 degree, right? Okay. So by dealing with by using phasors, actually we are able to calculate the values, the maximum value as well as the initial phase, okay, which otherwise is very impossible, very difficult task, which otherwise is a very difficult task, right? Okay, we directly use Ohm's law even for non-ohmic kind of thing. You know, capacitor is a non-ohmic thing, okay, but we can use Ohm's law, okay, with the use of phasors, but okay, with the use of phasors. So that's why I used phasors. It enabled us to do to use Ohm's law, okay. We have something, sir, can these where question regarding architecture field asked a 3D question. Architecture, what exactly is being asked? कौन पूछ रहा था? publishing. Okay, they won't. JEE means paper 2. ईमेल आईडी क्या करना है? Please post your queries on the helpline actually. Okay, I'll take up the queries on helpline. Okay, and all your other doubts regarding this what architecture thing, you know, I never studied architecture. It's just that I am good with some diagrams. I can draw. I'm like, I don't draw clean diagrams. I don't guarantee clean diagrams. Okay, so please post your queries on the helpline. I'll take the queries definitely. Okay, I give you my word. Next time class लेने आना है फिर से. Okay, so shall we continue on this? I assume online लोग हाँ ही कह रहे होंगे. अच्छा पार्ट 2 नहीं हुआ यार अभी तक. पार्ट 2 नहीं हुआ. कहाँ पे वो आप दिखाना ये this thing. हाँ. पार्ट 2 हुआ नहीं हुआ. ऐसा बता गए. Do they ask for email IDs? Okay. Okay, some professors have given email IDs. For that, you need to check emails regularly. Actually, I don't know whether I would be checking that regularly. Online people, post the answers. Anyone? Still no one? Someone is asking a question. Whiteboard is not clear. Whiteboard is not clear. आप brightness थोड़ा सा बढ़ा लीजिए. What exactly? 5. The whiteboard is not clear is the current question. I hope it would be clear now. 5V. Answer. Okay. No, 5 is not the correct answer. Something like 24 by 5 ऐसा कुछ. Anyone else? Is it that difficult? Huh? नहीं होगा 5. चलो अच्छा, let's start. Okay, I'll do it for you. Second question, second part. Okay, fifth question का. Fourth. Okay, second part. So let's do it. Let's try it now. It says the potential difference across points is half of the EMF. So we know that VAB at this point of time is 5 cos 100 pi t. Let's calculate VAB separately. Okay, between A and B we have this X, C or L, whatever it is, 2 and 8. Okay, this would have, acha, again, what would be the phasor diagram for C? L के XL के लिए ऊपर, ओके, XC नीचे, ठीक है। सो एक्चुअली डायग्राम और वैल्यूज उल्टी हो गई है, मतलब दिस should be L and this should be C, उल्टा हो गया, but still doesn't matter, you already know, ठीक है, you are smart enough। तो ये x होगा कितना 6, x होगा 6, तो x we can write 6 एंगल कितना प्लस 90 डिग्री, है ना, ओके। So we know XAB would be 6 plus 90 degree. VAB would be what? In phasor form, IXAB phasor form. Right? Right? I we have calculated 1 angle minus 37 degree. Okay. And X would be 6 angle plus 90 degree. So it would be 6 angle plus 53 degree. The angles would be added. In multiplication, the arguments are added. Okay, like complex numbers. So in sine form, it would be what? Omega t plus 53 degree. Right? Okay. So this value is actually equal to 5 cos 100 pi t, 6 sine omega t plus 53 degree. Omega, not omega, 100 pi t actually. Omega is given as 100. So 100 pi t plus 53 degree is 5 cos 100 pi t, right? Okay, can you expand this for me? One more thing, we started off with a cos, and so we should have a cos here, same things, right, comparatively. Okay, now expand. We started off with a cos thing, okay, it's not a sine, it's a cos thing. So in comparison with everything, angle 90, the current here would be cos omega 100 pi t minus 37, and everything it would be cos. Okay, expand it, क्या होगा 6, क्या होता है cos a cos b, cos 100 pi t cos 53 प्लस नहीं माइनस, सॉरी, हाँ, okay, and it is equal to 5 cos 100 pi t. Okay, okay, can we put the values? Cos 53 is 3 by 5 and sin 53 is 4 by 5. So 6 cos 100 pi t into 3 by 5. It would become, the thing would become 18 by 5 actually, minus 24 by 5 sin 100 pi t is 5 cos 100 pi t. Okay, okay, and now what you can do is you can separate the cos parts and the sine parts. You can calculate the tan thing, right? Go ahead, please do. Minus 7 by 5 cos 100 pi t is how much? 24 by 5 sin 100 pi t. Is it okay? And what? Tan 100 pi t, taking cos in the denominator, okay, is minus 7 by 24. So actually what is happening is some this sort of thing. We can assume it in the fourth quadrant or in the second quadrant. Okay, so let's assume in the fourth quadrant, makes the job easier, right? The value of tan is 7 by 24. So if you make a triangle, a right angle triangle, its base is, its height would be 7 and base would be 24. Okay, the hypotenuse would be 25. Okay, you can form a triangle. You can form a triangle of this sort. 27, 7, 27, 24 and 25. Okay, this is the phi. Sorry, 100 pi t, sorry, this is the 100 pi t, right? Okay, so for this triangle cos 100 pi t, what would be cos 100 pi t? For the same triangle, cos would be how much? 24 by 25, right? And this is what we need to calculate. Just replace the value 24 by 25. How much do you get? 24 by 5 volts. Okay, positive if we take fourth quadrant and negative if we take second, because in second quadrant what cos would have been negative. Is it okay? Right? If you wanna write, then okay. Did you expect it solved like this, totally mathematical way? Okay, the phasor makes this possible actually, otherwise to nahi hota. You have a question? Can we take it afterwards? This one topic. Huh? From what time? So you would have 2-3 minutes, right? I'll solve your question, don't worry. Shall I erase? हो गया है आप लोगों का? Shall I erase? Okay. Next is behavior of L and C with frequency, with variable frequency. L, L gives rise to omega L, okay, or 2 pi f L. Okay, so for low frequencies, what happens? For low frequencies, XL is low. Okay, for low frequencies, XL is low, which means in circuit the current would be high. It would allow a lot of current. Okay, okay, so I would be high. Okay, for high frequency, XL would be high and it won't allow current, I would be low. So that means if I feed a mixed signal, okay, if I feed a mixed signal, that means a signal containing low high frequencies, the inductor would filter out low frequency thing. It would allow the low frequency current to pass through but would block the high frequency. Okay, okay, so I can say from this thing, I can say This behaves as a short circuit for DC and open circuit for high frequency AC, high frequency kilohertz, megahertz. Okay, if I plot it graphically, the graph I would plot later. Actually, I'll plot one. I'll plot all three in one just. So because of this thing, that it can filter what? It can filter low frequency current components out of total. So this filtration, on the basis of this filtration, we call it low pass filter. Okay, it allows low frequency currents to pass, low pass filter. Okay, for C, it gives rise to 1 by omega C or 1 by 2 pi f C. Okay, now see what happens in low frequency scenario. Xc would be high. In high frequency scenario, Xc would be low. Okay, what happens? It would behave as open circuit for low frequency के लिए, you know, low frequency के लिए the reactance is high. It would block low frequency, which means for zero frequency it would be infinite open circuit. That means for DC it is open circuit. Okay, and it is short circuit for high frequency AC. Okay, short circuit for high frequency AC. And what should I call it now? It allows high frequency currents to pass. High pass filter. Okay, so it is high pass filter, right? Okay, if I draw the graph, you know, for resistance the value never changes. Whatever may be the frequency, it is not the value of our resistance is not dependent on frequency, right? Okay, so with frequency the value of R remains same. So if I draw graphically, I am drawing it here, please draw it separately, lack of space. Okay, if I draw R or X versus frequency, for resistance it would be a straight line. Okay, resistance keeping constant. For XL it would be an increasing graph. For XC it would be what? Exponentially decreasing, or what? It's a rectangular hyperbola. Inverse relation directly says it's a rectangular hyperbola. Okay, okay. So this decreases. This is the graph. Separate from the thing. Okay, done. Shall I erase? Shall I erase? Okay. RLC circuit, series RLC circuit. Okay, and let's have AC EMF across. Okay, you already know what would happen in this case. Let me draw the diagram. R, this is C, and this is L. The thing would become, first thing remains same R, second thing is boxed XL, third thing is boxed XC. And the phasor notation for these boxes are, first one would have this, okay, second one would have, you already know it, plus 90 or minus 90. अच्छा, अब confusion नहीं रहा. For XC, minus 90, okay. If we plot it, R here, XL ऊपर, XC नीचे. Let us assume X is here. So this is the impedance. You have already done a question on this, so we won't be spending a lot of time on this. X by R, which is XL minus XC by R. Okay. The Z in this case would be under root R square plus XL minus XC का whole square. Right? That's all. Correct? Chalo, we'll meet next time for the remaining topics. Just a few of them.